This is Duke University.
Hi, I'm Drew, and my colleagues and I would like to welcome you to Java Programming Solving Problems with Software. We here at Duke are so excited that you're taking this first step in learning to solve real problems using Java. In this course, you will learn a 7-step process designed to help you understand how to approach any programming problem. You'll use this process to solve real problems, and you'll learn that computer science is so much more than the syntax of a programming language like Java. You'll have a chance to work on problems such as analyzing DNA, manipulating CSV files, and processing images. These are real problems that engineers, scientists, programmers, and others work on in real life, and you too will be able to tackle these problems as you begin to learn Java.
I'm Susan. In this course, you'll learn to program in Java using techniques that can be used with simple programs, but that can also scale to larger programs and larger problems. The libraries and APIs we introduce make it easy to process data in many formats. You'll be able to use these same techniques, tools, and libraries in solving the problems we've designed for you. Problems whose solutions require the programming knowledge that you'll learn here.
I'm Robert. As you learn about the syntax and semantics of Java programs, you will practice with a programming environment that's been specifically designed and proven to help learners like you who are getting started in programming. This programming environment will let you design, test, run, and debug your programs using techniques that software engineers, scientists, and programmers apply as they design, create, and solve problems using Java and other languages. This programming environment can scale to large problems and is a great first step as you learn to master increasingly sophisticated concepts.
I'm Owen, and I'm really excited about the problems we've created for this course. We've used our collective years of experience to simplify problems and to provide you with opportunities to demonstrate your mastery of Java programming, while you work on real problems that are only slightly simplified from those problems faced every day by those working in the many fields that use computational and programming approaches. We've designed our Java libraries in a similar way, using standard Java idioms that you'll see if you continue to study programming, but that are more easily used by those just getting started with Java.
Once again, welcome to Java Programming, Solving Problems with Software. See you in the course!
Hi, I'm Elizabeth. I'm part of the instructor team here at Duke University. Before you get started with this course, I want to make sure you're aware of some important resources and give you some tips for doing well. The assignments in this course will be programming exercises, so you'll practice writing code. Anything labeled programming exercise here in the course content is an assignment and contains instructions to help you write your own program. When you've finished writing your code, there will be a practice quiz where you can check your program works properly by comparing your results to answers provided by the instructors. I also want to show you the course site, dukelearntoprogram.com. You can see we have a page for each course and a page of frequently asked questions about the specialization. This has everything from certificates to the software we use in the course. If you go back to the home page and select the course you're working on, you'll get to that course's main page. So I'm using course 2 here as an example. What I want to point out now are project resources, documentation, and the frequently asked questions page. Project resources is where you can download code to follow along with the video lectures or to begin the assignments. Documentation has a summary of the Java methods you'll learn in this course. This is useful if you forget the name of a method or if you want to find out if there's a Java method to accomplish a particular task. It's not an exhaustive list of all Java methods, it's just a summary of the most useful ones for this course. Finally, the frequently asked questions, or FAQ page, contains questions specific to this course. For questions about the specialization as a whole, click this link up here. So hopefully this video has given you an idea of how the course is structured and what resources you'll need to know about. If you have any feedback about how we can make these resources more useful to you, please let us know in the discussion forums on Coursera. To help you do your best, we want to give you some suggestions about how to learn in the course. First, do a little each day. It's really hard to learn programming all at once. If you do a few course items each day, instead of trying to do it all in a day or two, you'll remember things better, you'll be more motivated, and you'll have more time to work through problems in your code. Speaking of problems with code, also known as bugs, it's normal to make mistakes when you're programming. So our next tip is, don't give up. Everyone gets bugs in their programs, and part of programming is figuring out what's wrong and how to fix it. When you're programming, we really recommend following the 7-step process. This means you should plan how to solve the problem before you start writing any code. If you didn't take our first course, don't worry, there will be a chance to review the 7-step process later. The 7-step process is important because it gives you a method for solving problems. Then when you've figured out a solution, you can start writing code. Once you're ready to start writing your programs, make sure you've read the relevant documentation so you know what Java methods exist and how to use them. Refer back to the documentation as often as you need to. Next, take advantage of the live coding videos and the practice quizzes. For the live coding videos, this is a great opportunity to program alongside the instructors. You can also download the code from the videos and run it yourself. Try making small changes to make sure you really understand what each part of the program does. Finally, for the practice quizzes, even though they don't contribute to your final grade, there's still a good chance for you to test your code. Use the practice quizzes to find and fix problems before you move on to the graded quizzes. Finally, if you're still having trouble with your programs, ask for help from the instructor team and your peers in the course discussion forums. Part of being a good programmer is knowing how to ask for help effectively. We'll talk more about that in the next video. It's completely normal to struggle with learning programming, and when that happens, the instructor team and your peers in the courses are here to help. The best way to ask for help is through the discussion forums, which you can find here. You can also answer questions in the discussion forums, and we really encourage that, because explaining programming concepts is a great way for you to learn, and you also get to help out one of your classmates. Here are some general tips about asking questions in the forums. First, before you start a new topic, you should check the FAQ pages on DukeLearnToProgram.com and existing forum threads to see if your question has already been answered there. The first thing you should do when you have a question about a programming assignment or a quiz is check the FAQ page for that course. Second, start a new thread if you have a new question. Don't post your question as a reply to an existing thread unless it's really closely related. This way it's easier for people to see what your question is about and help you more quickly. Third, if you need to post code, use the code formatting box, which is the one with this symbol on. This is much easier to read than if you just copy and paste it directly into the post. We also want to give you some tips on writing a good question so that others can help you most easily. If you're having trouble with a programming assignment, name and link to the assignment you're working on. If your program is throwing an exception, you can post a screenshot of the error message and also the line of code that it occurs at. If your program is producing a result that's different from what you expected, make sure you say what input you're running your code on, the output you expected to get, and the output you actually got. For example, suppose I'm trying to write a program to change every green pixel in an image to blue. I should share the image I'm running my program on, my input. I should explain that I'm expecting every green pixel to become blue, my expected output, and I should also explain that every green pixel is actually becoming red, my actual output. Then others in the forum can better understand the problem I'm having. If you have to share some code because others can't help based on the description of what your program is doing, it's okay to share a few lines of code, but don't share your whole program. Figure out which part of your program you think the error is in, and share a few lines of that method. Don't copy and paste your whole program into your post. If you have a general programming question, such as how do I write a for loop, or how do I add items to a list, it's okay to post those lines of code because they're so general. Finally, if you have a conceptual question, make sure you name and link to any course materials you refer to. When you're answering questions, it's okay to share code for general programming concepts, such as how do I write a for loop. However, if someone is having a problem in their code, don't give them the solution. Try to guide them towards fixing their code themselves by giving hints. If you don't know what the problem is, suggest what they might do next to debug their code. Let's look at some example posts. In this post, I didn't really ask for help very well. I said my code wasn't working, and I asked if anyone knew what might be wrong, but I didn't really explain what the code is trying to do, what it's actually doing, or what troubleshooting I had tried so far. I also posted a lot of code. So I edited my post, and now it's much better. You can see that I explained which assignment I'm working on, and I provided a link to it. I also explained what happens when I run my program, so my actual output, and what should have happened when I run it, so my expected output. Finally, I only posted a few lines of code that I thought the problem was in. Now that you've learned how to ask and answer questions about your code, you're ready to start learning how to program. I hope you enjoy the course, and I look forward to interacting with you all in the forums. Good luck!
Hello. We wanted to take a moment to tell you about a specialization created by instructors from Duke University and the University of California, San Diego. It's called Object-Oriented Programming in Java. I'm Owen Astrakhan, one of the instructors from Duke University, and I'll be helping you learn this specialization. We're going to start from the beginning with Java and learn how to use it to write programs to solve a wide variety of problems.
I'm Susan Roger, and I'm another one of your instructors from Duke University. We'll start out with the basics in Java. So while we hope you have some programming experience already, we're going to assume you don't know anything about Java, but that you are eager to learn.
The next course of this specialization is Java Programming, Arrays, Lists, and Structured Data. I'm Robert Duvall, and I'm excited to be teaching you about Java. In our next course, you'll dive more deeply into Java and learn to store data in more complex ways, allowing you to solve even more interesting and exciting problems. I think there's even a dinosaur in one of our examples.
And I'm Drew Hilton, and I'm your fourth instructor from Duke. After you learn these Java fundamentals with us, our friends from UCSD will take over and teach you even more exciting things about Java and object-oriented programming. We'll let them introduce themselves to you now, and then you'll see them again in a couple of months.
Hi, I'm Mia Minnis. I'll be one of your UC San Diego instructors. You'll meet us when you get to the third course, Object-Oriented Programming. In this course, we'll build on the programming concepts you learned from our friends at Duke, and then we'll also talk more about the object-oriented nature of Java and how you can use it to build bigger programs to solve more complex problems.
Hi, I'm Leo Porter, and I'm an instructor at UC San Diego. Another topic that you'll be learning in the third course of the specialization is graphical user interfaces and event handling. With these skills, you'll be able to build interactive applications that are both easy and intuitive to use.
I'm Christine Alvarado, the final instructor on the UC San Diego team for this specialization. I want to tell you a little about the fourth course in the specialization. In that course, you learn how to store data more efficiently so your program can quickly perform operations on large sets of data. By the time you finish that course, you'll be a pretty good Java programmer. So let's get started.
Hi. In this lesson, we're going to introduce you to Java programming and the BlueJ environment we use in this course to design, develop, test, and run Java programs. Java is a popular and widely used language. It is the foundation for the Android operating system that powers more smartphones than any other system in the world. Java is an extremely useful and quite powerful language, with extensive support on almost every kind of computer. Java is also accessible to beginners, which is why we're using it in our courses. At the end of this lesson, you'll have experience with BlueJ, the development environment we use for programming with Java. You'll be able to use BlueJ to compile and run a Java program. You'll know the basic design, edit, compile, and execute cycle that's part of programming with hundreds of different languages. And you'll see firsthand how simple and powerful Java is in accessing information that will print "Hello World" in many languages. This is our take on a traditional first program. We'll explain that more as you begin your exploration of Java programming. So, hola mundo, konnichiwa, zdravствуйте, ni hao, and hello world. Let's get started.
Hello, world of learners. In this video, we will look at how code is organized in Java and how programs are executed by the computer. We will also demonstrate how to run programs in BlueJ, the programming environment you will use in this course. Java is an object-oriented language. This means you'll use classes and objects in writing your code. Classes are a way of organizing your programs, and objects are created using classes when your program runs. We'll learn more about objects and object-oriented programming in the next course. Classes have a .java file extension. In a Java class, you will write one or more Java methods, instructions for your computer to carry out when you run your program. The code you write is called source code. Source code is high-level code, which is human-readable but not machine-readable. So when I open this Java class here, I can read the Java program one of my fellow instructors wrote in it. Now, in order for the computer to run my program, my source code must be translated into low-level bytecode, which is machine readable. Bytecode files have a .class file extension. This process of translating source code held inside classes into bytecode is called compilation. When you write Java programs, before you run your program, you will need to compile it. So, where do you write this code that will eventually be run by the computer? Programmers write code in programming environments. In these courses, we'll be using a particular environment called BlueJ. We chose BlueJ because it's a great programming environment for novices. It allows you to start programming without having to worry about editor complexities. And we've added some special features that you'll use as you develop Java programs for this course. You're going to run your first Java program. We're going to show you how to download it from the Duke Learn to Program website and then open up BlueJ and run the program. So I have the Duke Learn to Program website up right here, and we're going to go to Course 2 and click on there. There's lots of resources that we have provided for you on this website. Since we're going to run a particular project, we'll click on Project Resources. And here you can see our first program called Hello World, the BlueJ project. I'm going to click on that, and that is going to give you the Java program and the data file. So if you just click on that, it's a zip file, and we'll just unpack it and you'll have everything there. So I am now going to start BlueJ. So you should have already installed BlueJ. I'm going to click here, and BlueJ is going to start. And for me, I've already got the program there, but if you don't see it, you may have to click up here on Project and Open Project, and you'll have to go to where your project downloaded to, which folder it's in. Once you have it there, you'll see Hello World. So let's click on that and see what's there. This is your Java file. And here you can see the code for this. I'm just going to scroll over so we can see a little bit more. So this is a class, Hello World, and it has one method in it called run hello. And this is a very simple program. What we're going to do is we are just going to open up a file and we're going to print every line in the file. Each line in the file is a greeting from some country. So we're going to create a file resource, and you can see we're going to tie it to the file called hello_unicode.txt. We are going to assign it to a file resource called res. And then what we're going to do is we're going to loop over the file. So we have a for loop where we are going to, every time we call the file resource res.lines, it gives us another line from the file. We're going to assign that line to the variable called line, and then you can see the line inside the for loop is going to print that line. So that's what our program does. In order to run the program, we are going to right-click on Hello World here. You can see all the diagonal lines there. That means we haven't compiled the program yet. You need to compile the program so your computer can understand it. So we will right-click here, and there's a compile, so we'll compile it. If everything works good, you see the slanted lines disappear except for just the two in the right corner. And then that means it's compiled, it's created the class file, which is a machine readable code that the computer understands. So now we can right-click on that and create an instance or an object. You can give it whatever name you want. I'm just going to leave that name there. And so the object has been created, and now we can run it. So I'm going to right-click on here, and you can see that method, run hello, is right there. I'm going to run it. And voila, we have just printed all the lines from the file. And you can see all these wonderful greetings here. We have hello, hello, bonjour, guten tag, aloha, all of these nice greetings. Now I want to show you where these come from. There is a file that you are also downloading and I have a copy of it right over here. Let's see, let me get this. So this is the file, hello_unicode.txt, and you can see the exact same lines that we printed here. All here. Bonjour, Guten Tag, Aloha, all of these are right here. So our program, again, let me just come back to our program right here. Again, just real quick, we open up the file. You saw the file. We go over the file. We create a file resource and go through one line at a time in the file. We grab the line and we print the line. And that's it. So hopefully you've gotten your program to run, your first Java program, and you've enjoyed it. Thank you.
Hello, we're going to learn how to calculate the perimeter of shapes using Java. We'll use what is called a Java class, which you'll learn more about soon, named shape, to model polygons in geometry. These kinds of shapes are used in many applications. For example, a triangle is the simplest polygon or shape. It's simply a collection of 3 points. But triangles can be combined into complex shapes that are colorful or form the basis of wireframe diagrams used in computer graphics and video games. We'll use a shape Java class to represent a collection of points. We'll use a class for point and for shape to understand programming concepts that are applicable across many programming languages. We'll need to construct shapes by adding points one at a time. This will allow us to create shapes like this 6-sided shape, which is constructed from 6 points. Here is a shape with 5 points. Here is another 6-sided shape. The order in which the points are added to the shape is important. When we look at the code for the Java shape class, we'll also need methods for accessing the points, either one at a time or using other approaches. We'll likely want to create operations or methods that use shapes, like drawing a shape or finding the perimeter of a shape. We've seen that shapes can have many points. Our shape class is simple, but we could expand it to create complex shapes of many, many points, like this butterfly. When viewed more closely, it's clear that the butterfly is simply a collection of colored triangles, like the wireframe drawing we saw earlier. The shape class we'll look at is very simple. Circles aren't really a finite collection of points, so circles and some other shapes are harder to model using our Java class. In geometry, a circle is an infinite collection of points that are all the same distance from the center of a circle. Our Java class is just a finite collection of points. However, even with our simple class, we could model a circle using many points as shown in the diagram here. So even our simple class will prove very powerful. After we cover some of the basics of writing programs in Java, we'll explore the point and shape classes in more detail.
Okay, you will be using the Java classes shape and point, but what will you be able to do with these classes? Well, in some ways, you know the answer to that. You will be able to draw shapes or calculate a shape's perimeter, but just knowing what a Java class or script can do does not mean you understand it. So the question we are going to answer now is, how would you understand what this code does by yourself? That is, what are the semantics or meaning of each part of the code? Understanding the precise meaning of code is important because you can't write code without saying precisely what you mean. When we talk about understanding the semantics of code, what exactly do we mean? We mean, how would you execute the code by hand with nothing but pencil and paper? This skill is very important for a couple of reasons. First, it's how you understand code well enough to write what you mean. Second, when your code does not behave as you expect, how do you figure out what is going wrong? You need to understand what it does, and this gives you the skills to do that.
Hello, we're going to start learning to execute code with the most basic statements in Java and build up to more complex statements from there. Here we have 2 variable declarations, one for an int called x and one for an int called y. If we execute these statements as is, we will create boxes labeled x and y to hold the values we eventually decide to put in these variables. But In this example, we have not explicitly provided any initial values. In some languages, such as C, no default value is ever provided when you declare a variable, meaning you get undefined behavior if you use an uninitialized variable. This is such a common and significant problem that Java provides two solutions. An initial default value of 0 is given to instance variables, or an explicit error is given for using a local variable before initializing it. We will see these different types of variables in upcoming videos. Now let us look at another example, which initializes the variables when they are declared. Here, the first statement declares an int called x. Executing it makes a box for x and immediately assigns the value 4 to x. We show this by putting 4 in the box for x. Executing the next line both creates a box for y and puts the value 6 in that box. Combining the declaration and initialization of your variables into the same statement won't pose a problem in any language, and anyone reading your code knows exactly what you meant for the code to do. So this is a good habit to get into. Of course, variables are only useful if you make use of the value that they have. Here, the first code declares x and initializes it to 4. Next, y declares and initializes it to x plus 2. To perform this statement, we must evaluate the expression on the right-hand side of the equal sign. X is 4, so x plus 2 is 4 plus 2, or 6. We show this by creating a box for y and putting 6 into it. The last statement creates a variable z and initializes it to y minus x. So you would take the value of y, which is 6, and the value of x, which is 4, and subtracts them to get 2. You would then create a box for z and initialize it to 2. Great! Now you know how to execute code with variable declarations and assignment statements.
Now that you know a little bit more about expressions, let's see them in action. This code example starts with the declaration of an integer or int variable called x, which behaves exactly as you've already seen. Next, we initialize x to 4 plus 3 times 2. As you know from math, times has higher precedence than plus. So this expression evaluates to 4 plus 6, which is 10. So we put 10 in the box for x. Next, we declare another variable y of type int and initialize it to x minus 6, which is 10 minus 6, which is 4. So we create a box for y and put 4 in it. The last statement says x gets x times y. Sometimes novice programmers expect statements which look like this to behave like algebraic equations with an equal sign, where you might solve for x. However, that's not what happens. Instead, you follow the rules you've already learned. The right-hand side evaluates to 10 times 4, which is 40. And you put 40 in the box for x. Now, let's see another example. Before we work through this, take a moment to pause the video and see if you can figure out what values x, y, and z have at the end of this code fragment. Okay, let's step through it. First, we declare an initialized x. Next, we evaluate x times 3, which is 6, and initialize y to that value. Next, we compute y divided by 2, which is 3, and initialize z to that value. The last statement says x gets 2 plus z mod 2. Since the 2 plus z is in parentheses, we compute that first and get 5. Next, we compute 5 mod 2. Remember from your reading that 5 mod 2 means we divide 5 by 2, but take the remainder, not the quotient. So this expression evaluates to 1. So we update the value in x's box to be 1. Okay, great. Now you should be able to evaluate code involving a wide variety of mathematical expressions.
The next important idea to understand is function calls. Functions abstract a computation out, giving it a name and parameters. You then can use the function to perform that computation without rewriting it. You can also think about what the function does and not how it does it. Technically speaking, Java doesn't have functions, it has methods, since all code in Java is inside of objects. However, before we learn the more complex behavior of objects and methods, we'll learn the basic principles of function calls. These concepts will then lay the foundation for understanding method calls. We have three functions here: my function, f, and g. Why are we starting at g? We'll assume for now that you chose to call g from the BlueJ interface. Later, you'll learn about the main method, which is where programs start when you run them outside of BlueJ. We start with a frame for g, and with the execution right at the start of that function. The first line declares a, so we create its box inside of the frame for g. Next, we're going to set a equal to the value of the function call myFunction of 37. To evaluate this expression, we need to create a frame of the function that we're calling. In this case, myFunction. This will hold the parameters and variables of my function. Next, we pass the parameters to my function. We create a box for each parameter with the names coming from the function declaration, x and y. We initialize these by copying in the values of the expressions that were passed, here 3 and 7. Next, we need to note where to return when we finish executing my function. This location in the code is named the call site, the place where the function was called. We'll note it with the marker 1 in the code and put the same marker in the corner of the frame. Finally, we move the execution arrow into my function and start executing code there. Here we declare and initialize z, evaluating the expression 2 times x minus y. The values for x and y come from the frame for my functions, 3 and 7 respectively. So z will be -1. Now we have reached a return statement. Return statements tell us to leave the current function, returning to the call site noted in the frame. They also tell us the value to return to the caller. The first thing we need to do is evaluate this expression to obtain the return value. Here the expression is z times x. So we evaluate -1 times 3 and we get -3. Next, find where we should return. This is the call site we noted in the frame. Then we copy the return value back to the call site. The function call evaluates to this return value. We move the execution arrow back to the call site and destroy the frame for the function we just returned from. Now we're back in G. The call to my function evaluated to -3. So this line behaves like a gets -3. We'll finish that assignment putting -3 in its box. Our next line again has a variable declaration and a function call. We make a box for b and go through the same process to call f. We make a frame for f and pass parameters. This time there's one parameter in whose value is a times a, which is 9. We note where to return and begin executing code inside of f. Our next statement is a return statement, but the expression involves a function call. So we have to evaluate that call before anything else. We start with a frame and pass parameters. X gets a value of n, which is 9, and y gets a value of n plus 1, which is 10. We note the call site, we'll use 2 this time, since we were already using 1 somewhere else, and move the execution arrow to the start of my function and start executing code there. We declare z and initialize it to 8. Now we are ready to return from my function. We evaluate z times x, which is 72. Then we find the call site noted in the frame and copy the return value there. Finally, we move our execution arrow back to the call site, destroying the frame for my function. Now we pick up where we left off in f using 72 for the value of the call to my function. We evaluate 3 plus 72 to get 75. Since we're evaluating the return statement, this is the return value of f. So we find the call site and copy the return value there. Then we return to that call site, destroying the frame for f. Now we can finish the initialization of b. b gets 75. Lastly, we reach the return statement for g, which is where we started. When we return from the function where we started, we are done!
Now, let's see how to execute code with conditional statements in it. Here, we have a function f, which has some if and if-else statements. We have another function g. We'll assume we've used BlueJ's interface to invoke the method or function g to start with. The first statement declares a variable a, so we'll make a box for a. Even though this statement initializes a, it's going to take us several steps to compute that value. So we're going to leave a's value as 0 until we compute the value of the method f applied to arguments 3 and 4. To evaluate this call to f, we make a frame, passing the values of the parameters. Note where to return, and then we move the execution arrow to the first line of F. The next line of code is an if statement, whose conditional expression is x less than y. We evaluate that expression and find 3 less than 4 is true. So we move the execution arrow into the then clause of this if statement and continue executing. The next statement is a call to system.out.println, which is how you print something in Java. We write x less than y in our output, and then we return y plus x. This follows the same rules you've already learned for return statements. We evaluate the expression to get the return value, which is 7, which is then what the function call evaluates to, and we return back to the caller, destroying the frame for f. Now we're ready to finish initializing a, since we know that the call to the method f evaluated to 7. So a is now 7. Now we're ready for the next line of code in G. We make a box for b, and we call f, passing in the arguments 7 and 5. Once again, we want to evaluate the condition x less than y. However, now x is 7 and y is 5, so x less than y is false. We find the closed curly brace for this if statement and see that the if statement has an else clause. So we move the execution arrow into the start of the else clause and continue executing from there. First, we see the system.out.println statement, and this prints the line x is greater than or equal to y. Then we reach another if statement. This if statement is nested inside of the else, but that doesn't affect the rules of how we evaluate it. We see that the conditional expression is false, since 7 is not greater than or equal to 8. There's no else clause, so we move the execution arrow immediately past the closed curly brace and continue execution. There are not any more statements inside the else clause, so we move the execution arrow outside of the else clause and keep going. Next, we have a return statement. So we evaluate the expression x minus 2 to find that the return value is 5. This then gets returned to the place we noted. So we destroy the frame for f and return back to G. We finish the assignment statement, and now we're ready for the return statement from G. We execute that, and we're done with the method G.
As you continue learning how Java works, it is important to talk for a bit about objects and classes. Before we delve into the specific semantics, let's talk for a minute about the high-level concepts. When you are writing a program, you often have data in the form of variables which store the values you are computing on, and code which manipulates that data according to the algorithm you have designed. Object-oriented programming is a paradigm of programming languages that groups data and the code that manipulates it together into logical units called objects. This language design aims to help programmers think about their program by grouping the code and data together into one logical unit. As you write larger and larger programs, this principle becomes more and more helpful. As you progress and learn more about Java, you will learn about a lot of important principles that go along with these ideas. For now, however, we are just going to start with the basics. Here, you can see an example of a class declaration. A class is a template that specifies how to make objects. Let's look at each piece of this declaration. The first line tells Java that we are declaring a class called point. As with variables, we have a lot of freedom in what we name classes that we create, but we should name them descriptively. Here, we are making a class which represents a two-dimensional point, so point is a good name for it. Next, we declare two fields, int x and int y. Field is the name for a variable that is inside of an object. They are also called instance variables, since they are variables that are in each instance of the objects created from the class. These look like variable declarations, except that the word private comes before them. Private means that only code inside of this class can directly manipulate these fields. You'll learn more about why that is important as you become more skilled in Java, but for now, we'll just make all fields private. Next is the declaration of a constructor for the class. A constructor specifies how to create objects of this class. It is code that gets run when an object is created to initialize that object. Note that the constructor looks like a function but has no return type. and is named the same as the class. These are the hallmarks of a constructor declaration. In front of the constructor, we have the word public, which means that any code can use this constructor to create a point. After the constructor, we have three methods: getX, getY, and distance. Methods are functions that are inside of classes. In Java, everything is inside of a class, so technically all functions in Java are methods. These methods are invoked or called on a particular object and implicitly act on that object. You can see a method call here where the code says otherPoint.getX. This calls the getX method on the otherPoint object. It will get the x of that particular point object. Last, we have the declaration of a static method. These behave a little differently from regular methods. They don't act on any particular instance of the class. They just belong to the class in general. That concept is a little tricky, and we'll explain it more later. This method is called main, which is a special method. If you run your programs outside of BlueJ, main is the starting point. Execution begins in main before any objects are even created. The ideas of objects are supposed to help programmers think about their data in terms of objects that make logical sense. For example, if we make a new point, we are creating an object which represents something we can concretely think about. In this case, a point on a plane. We can then make another point which has its own x and y and represents a different instance of the same type of thing, another point on the plane. You can of course create as many of an object as you need for your algorithm. Once you have some objects, you can invoke methods on them, such as p1.distance p3, which you can think of as asking p1 to compute the distance to p3. That is, you can think of this line of code as saying, P1, go figure out how far you are from P3. You can think of the code that executes for this method call as logically belonging to the P1 object. Now that you have the high-level concepts, let us delve into the step-by-step execution of our example point code. We're going to start in main, which we'll talk about more later. Args gives you access to the command line arguments, which you won't need for quite a while, so we are just going to ignore that. The first line declares point P1 and initializes it to a new point. Note that classes are types, so we can use class types that we make to declare variables. Here we want P1 to be a point. Until we finish evaluating the right-hand side, we're going to draw this as an arrow with a flat end. We'll use this notation to indicate when a variable does not reference an object. Note that this is a bit different from numeric variables like ints, whose initial value is 0. We've colored this flat-ended arrow red to remember that we have not yet explicitly initialized this variable. Now, let us evaluate the right-hand side of the initialization expression. We are doing new, which will create a new object. What type of object are we going to create? We look right after new and see that we are creating a new point. So we are going to draw a box for a point which has fields x and y. Note that the box we just drew is not in the frame, but is outside of it. It is in a different area called the heap. Anytime you use new, you create data in the heap. The important difference is that data in the heap does not go away when a function returns, destroying its frame. Note that we have put 0 in the fields of this new point and colored them red as we have not explicitly initialized them yet. Speaking of initialization, remember that we said that the whole point of a constructor is to initialize a newly created object. The next thing that happens is that we call the constructor to initialize this point. As with any call, we set up a frame and pass parameters. However, constructors and methods take an additional implicit parameter which tells them which object they are operating on. That parameter is called this, and its value is an arrow which points at the object that is being acted on. In this case, this points at the object that we are creating to tell the constructor which object to initialize. Now we enter the code for the constructor and begin executing statements there. The first line says x gets start x. There's no x in this frame, so where do we store the value of start x? Here, x refers to the field inside of this object, That is, we want to put startX's value into the x field of the object we are initializing. So to find the right box, we follow the arrow for this, and then look for the x field in this object, and store the value 3 into that box. On the next line, y again refers to the field inside of this object, so we update that field to be 4. Now we have finished the code inside the constructor and are ready to return to main at call site 1. Back in main, we need to finish this assignment statement. To do that, we need to store the value of the right-hand side into the box for P1. A new expression evaluates to an arrow pointing at the object that it created. So we will make P1 to point at the newly made point. The next line does a similar thing. It declares P2 and initializes it to a new point. So once again, we create a box for P2. We haven't initialized it explicitly yet, so we have a default value of a flat-ended arrow, meaning it does not point at any object yet. We color it red to remember that it is a default value. We then create a new point with its x and y fields set to default values of 0, and we call the constructor to initialize this point. Notice how this points at the newly created point. With multiple points in our world, it is important that we can keep track of which point we are working on. We then initialize the x inside of this point to be 6. As before, we found the right box by following the arrow from this, and we initialize the y inside of this point to be 8. Now, we have finished the constructor and are again ready to return to main. In main, we finish the assignment statement setting P2 to point at the newly created object. We'll stop there and pick up with executing the method call in the next video. In the previous video, we executed the declaration and initialization of points P1 and P2, and you learned about new and constructors. Now, it is time for you to learn about method calls. Method calls work a lot like function calls, except that we have to pass the this parameter to let the method know which object it is working on. Let us resume where we left off. This line is going to call p1.distanceP2 and then print its return value. We need to set up a frame for distance, which will take 2 parameters. The implicit this parameter, which tells it which object it is acting on, and the other point parameter, which is explicitly passed to it. The this parameter has the same value as the variable before the dot. In this case, we have p1.distance, so this has the same value as p1. It is an arrow pointing at the same point object. We have colored this arrow differently, but that does not have special meaning. It is just to help you keep straight which arrow is which in this diagram. For the other point parameter, we just copy the value that is passed in this case, P2. So the value of other point is an arrow pointing at the same point object as P2. Now, we go into the distance method and begin executing code there. Executing the first line, we are declaring a variable dx and need to initialize it to x minus other point.getX. To evaluate that expression, we need to call other point.getX. So we need to set up a frame for that method call. Again, this method takes an implicit this parameter to tell it which object to do getX on. Which object should this point at? Well, we did other point.getX, so we copy the value of other point, which is an arrow pointing at that point object. Now we go inside of getX and begin executing code there. Here we have return x, so we need to evaluate the expression x and return its value. How do we get the value of x? We follow the this pointer to find the object we are working on and then look for the x field inside of that object. The value of that field is 6, so that is the value of the expression x here, which is what we'll return to the caller at call site 2. Returning to call site number 2, we want to evaluate x minus 6. How do we evaluate x here? We again look at the this pointer, which refers to this point object. And we get the x field inside of that point object. That value is 3, which is the value of x in this expression. So we will compute 3 minus 6 and initialize dx to minus 3. Now we are going to declare and initialize dy using a very similar process. First we make a box for dy, then we call getY on other point. Notice how this is a copy of the value of other point, an arrow pointing at our second point object. We get the value of the y field out of this object, which is 8, and return it to call site 2, where we return the execution arrow to. We evaluate y by looking in this object and finding its y field, which is 4. Now we are ready to finish the initialization of dy to 4 minus 8, which is negative 4. Our next line has a little bit of math. Let's look at it in detail. We are calling math.square root of dx squared plus dy squared. First, we can compute the value of the parameter, which is 9 plus 16, which is 25. So we need to evaluate math.square root of 25. This looks like a method call, but where did the math object come from? It turns out that math is a class, not an object, and is part of the Java library. This is a static method call. The method is being called on the class in general, not on any particular object. Here, the math class is just a handy place to put a bunch of mathematical functions together. Since we don't have the code for math.square root, we have to know what effect it has. If we did not know, we would look it up in the Java documentation. However, as you might have guessed, this method just computes the square root of its argument. So math.square root of 25 will return 5.0. Our distance function returns that value to its caller, so the value of the call to distance in main will be 5.0. We then return execution to main, where we are ready to complete the print statement, which will print out 5.0. Now we are done with main, so we will return from it, destroying its frame and exiting our program.
At this point, you have seen a variety of types such as int, point, and file resource. But what exactly is a type? A type specifies how data should be represented, interpreted, and operated on, as well as what operations you can do with it. One important rule of computing is that everything is a number. If you didn't learn about the everything is a number principle in whatever intro courses brought you here, we'll give you some links to videos about it. Specifically, this means that everything is stored in the computer's memory as bits, ones and zeros. But not all numbers mean the same thing. Some numbers might mean plain numbers, while others might mean letters, and others might mean the locations of data in the computer's memory. So the type of a value specifies how to interpret those numbers. It tells Java how to assign meaning to the ones and zeros stored in memory. The type also specifies what operations you can perform on the data. The type tells Java not only what you can do, but how it should be done. Let's talk about both of these points in more detail. We just said that the type tells Java how to interpret the ones and zeros in memory. Let's talk about that a little bit more. On the left, we have the conceptual representation of the program state that we have been working with. There's a box for a variable called x. On the right, we have a bunch of bits from the computer's memory. The blue ones correspond to x. But what do they mean for the value of x? Well, if x is an int, then these bits would mean it has a value of 1,234,567,890. We're not going into the details of how you can figure that out here, nor do you need to know it for beginning Java programming. But if you take a computer organization class, you will learn a lot more about how data is represented. The point we want to make here is that if x had a different type, like float, then the same bits would have different meaning. These same ones and zeros would mean 1,228,890.25. And if x were a string, then the bits would be the location in the computer's memory of the actual string object, which would have a sequence of characters. Those would also be stored with a bunch of bits that would be interpreted as letters, since their type would be char. We also said that the type tells us what operations we can do and how they're done. Consider this simple bit of code. X plus Y. Is it legal? And if so, what does it do? To answer this, you need to know the types of both X and Y. If X and Y are both ints, then this code is legal and performs integer arithmetic. If X and Y are both strings, then this code is also legal but performs string concatenation. It makes a string with the letters of X first, then the letters of Y immediately after. Notice that even though the plus operation is legal for two different types, we may perform that operation differently for one type than for the other. If X and Y are both points, then this code is not legal. While we're talking about types, you might be wondering what you do if you need to convert between types. The answer is that it depends. For some type conversions, they can happen implicitly. If you have an int and you need to convert it to a double precision floating point number, the compiler will just automatically insert the conversion for you without complaint. The general rule is that you can use implicit conversion whenever the compiler will consider it safe. Here we are turning 3 into 3.0, which is not a problem. Note that the compiler does not consider the values, only the types, when deciding if an implicit conversion is okay. For some type conversions, you can explicitly cast. This means that you tell the compiler that even though what you're doing is questionable, you are sure you want to do it. Here we are turning the double 3.14 into an int, which will discard the fractional part, leaving us with x equals 3. The compiler wants to be sure that we meant to do this, so we explicitly cast by writing int in parentheses. Other conversions require calling methods to calculate out the converted value. For example, if we have the string quote 3 quote and want to turn it into an integer, we can't just directly cast it because the conversion is actually somewhat complicated. Instead, we have to call a method like integer.parseInt, which will perform the conversion. The last thing we will mention about types is that there are two major categories of types in Java: primitives and objects. There are 8 primitive types: int, double, char, boolean, long, float, byte, short. We'll primarily use the first 4 of these. Variables of primitive types hold their value directly in their box. Primitive types don't have methods, so you can't do .method call on a primitive, and they can't be null, although each primitive type has an associated wrapper class, which gives you an object to hold that primitive. Everything else is an object type. Some are built into Java, like string. Others are part of libraries that you might use, like point or file resource. And yet others are classes you will create yourself. Whenever you make a class, the class you make is its own new type. Unlike primitives, the value of variables of object types is an arrow pointing at the object. This arrow is called a reference. You can invoke methods on the object with .method name, and the reference can be null, meaning it does not refer to any object. If you do equals equals on 2 objects, you're checking to see if the arrows point at exactly the same object. Okay, that's the basics of types. We know it's a lot to absorb at once, but you'll get better with these ideas as you practice more Java.
Hi. Now we're going to learn how a for each loop works. This piece of code looks similar to the hello around the world example that you started with earlier. To make this work, we need to add an import statement to the top to tell Java where to find the file resource class. File resource is in a package that we provide to you to let you manipulate data in files before you learn the more advanced techniques and concepts that would let you do this in Java directly without the classes we've created. Accordingly, this is found in the edu.duke package. If you want to run this code in BlueJ, you could do so by creating a hello world object and then invoking its runHello method. We could also add a main method, which does the same thing if we want to be able to run the code directly but outside of BlueJ in another environment. Let's start executing the code by hand. We start in main with a frame that contains args. We're not going to use this args argument, so we're not going to worry about its value. The first line declares HW and initializes it using new. You learned about new in a previous lesson, but there's a slight difference here. The Hello World class does not have a constructor. So what do? In this case, Java provides a default constructor, one with no arguments, that does nothing. So we execute this line as you're used to, but we don't call a constructor. We make an object. Class Hello World has no fields, so the object itself doesn't have any state or anything else we can see in it. Then we finish the assignment statement. Next, we call runHello, passing in HW as the implicit this argument. Inside of runHello, our first statement declares the variable f. The next statement initializes f to a new file resource object. This raises two questions. First, what does a file resource object look like? Meaning, what fields are there in the file resource object? It turns out we don't actually need to know this precisely. The details of how a file resource object works can remain hidden from us as long as we know what it does. This is an instance of the important programming principle known as abstraction. Second, what does the constructor for a file resource object do? To find the answer to this question, we would consult the documentation for file resource. Consulting documentation for libraries, sometimes called APIs, that you use in programming is an important task. Since file resource comes from the Duke Learn to Program libraries, we would look at the documentation website and we would read about the constructors for a file resource class. There are 3 constructors, and the one we want is the one in the middle, since we're passing a string literal in, the string, quote, file.txt, quote. This documentation says the constructor will find that file with that name on our computer. Given this information, we're just going to represent the file resource object as knowing what file we asked for, the file whose name is, quote, file.txt, end quote. We don't know precisely what fields are stored in this object, but that's okay. We'll represent it as precisely as we can because we know what the object does. We finished the assignment statement, so now f references this file resource object we just created by calling the constructor. The next line is new to us. It's a for loop. In particular, this for loop is often called a for each loop because it does something for each value in an iterable. What's an iterable? The short and simple answer is that it's an object which gives you a sequence of values. Let's dig a little more closely into the details of this loop. The first part declares a variable. The type is string and the name of the variable is line. This declaration will behave like any other. We'll create a box for line. Next is a colon. This is the syntax of a for each loop. We don't use an equal or assignment operator since we aren't assigning one value to line. Instead, we're going to use each value in the iterable sequence. Many people read the colon as in when they read the code out loud or to themselves. For string line in f.lines. Next, we have an expression which evaluates to the iterable whose values we want variable line to refer to, one after the other. In this case, that expression is a call to f.lines. To understand what this does, we'll need to understand what f.line returns. So we'll again need to consult our documentation. From this API documentation, we see that f.lines gives us an iterable, whose values are each line in the file in the order that they appear. This means that we'll need to look at the file whose name is file.txt to see what its contents are in order to understand and simulate the code behavior. On my computer, I've made file.txt and put these 2 lines in it, hello on one line and world on the next line. It isn't a very exciting file, but we want this example to be relatively short. Returning to our code, we now create this sequence of strings, hello and world. We'll create the box for line, and we'll make it refer to the first element of this iterable sequence. Now, we go into the body of the for loop and begin executing statements there. The next line is a print statement, so we print out the value of line, which is hello. Now our execution arrow is just before the close curly brace of the for each loop. We've reached its end. When you reach the end of a for loop, you move the execution arrow back to the start of the loop to do the next iteration, the next time through the loop, with a new value for the loop variable. In this case, our loop variable is the string line, so we need to update it to have the next value in the iterable. we update line's arrow to point at the next value in this sequence, and again go into the body of the loop. We encounter our print statement, but this time line has a different value, so we print world. Now we've once again reached the end of the body of the for loop, so we go back to the beginning, the start of the loop. We need to update line to refer to the next value in the iterable sequence. However, if we try to do that, we'll find that there are no more elements in the iterable sequence. We already used the last one, so instead we exit the loop. We move the execution arrow past the body of this for each loop and begin executing code there. When we do this, the loop variable, in this case the string line, goes out of scope. That means it no longer exists, so we remove its box. Now we're ready to return from the method runHello, destroying its frame. Since the call to that method runHello was the last line in main, we also return from main, exiting the program.
Today, you're going to learn how to solve programming problems using the 7-step approach that we will use throughout the rest of this course. When you're solving a problem, you're going to start with a problem statement. You know that you want to end up with working code, but going straight from a problem statement to working code is a rather large leap. It can take some significant thought and work. This is why we break it down into 7 steps for you, giving you a manageable approach where you know what to do next to solve the problem. This is the 7-step process that we recommend you use whenever you are solving programming problems that are difficult. As your programming skills improve, many problems will become easy enough to just do them in your head. However, there will always be some problems that are harder, and having a step-by-step approach will be helpful to you. Let us look at each step in a bit more detail. The first step is to work an example of the problem yourself, by hand. This should be a small instance of the problem, something with about 4 or 5 pieces of data to manipulate. You don't want to try to process 1,000,000 pieces of data yourself. That would take forever. If you have trouble doing the problem yourself, you cannot write a program to do it. So what should you do if you get stuck here? Well, one of 2 things could be wrong. Maybe the problem is just unclear. The problem statement does not give you enough information about what you're supposed to do. In a classroom setting, you could consult your teacher or TA. In a professional setting, you might work with your technical lead or customer to clarify the requirements, or you might just need to refine the problem statement yourself. The other potential problem is that you lack domain knowledge, the knowledge of the field that the problem belongs to. If you're trying to write a program to compute physical motion, and you do not know the physics equations that you need, that would be a lack of domain knowledge. When you have this sort of problem, you need to find the relevant domain knowledge before you proceed. In step 2, you want to write down what you just did to solve this problem. You want to be as exact as possible. Do not leave anything out, and write down how you solved it in a step-by-step fashion. At this point in the process, you are just writing down the step-by-step approach for the one particular instance you solved, not the more general problem. The tricky part in this step is that we often do things without thinking about them. If you gloss over something or you're not precise about what you did, it will make the later steps harder. In step 3, you want to move from the particular instance that you solved in step 1 to an algorithm that works for any instance of the problem. That is, you want to devise an algorithm which can solve the problem correctly for any input that you give it. You'll do this by finding patterns in what you did and replacing specific behavior with more general behavior based on that pattern. Some important tools for finding patterns, which we will delve into more deeply soon, are looking for repetitive behavior, finding behavior which you do sometimes but not always, and figuring out under what conditions you do it, and figuring out how specific values you use relate to the parameters you picked. So what should you do if you have trouble with this step? Go back and try steps 1 and 2 again. Use different inputs, which will give you another example to work from. You can see the steps for a different instance of the problem and have more information to help you find the patterns. In step 4, you want to check your algorithm. before you proceed to turn it into code. If you found the patterns incorrectly or otherwise made a mistake in step 3, you would like to find that out now. The way you check your algorithm is to pick at least one different input. Again, it should be a small one. And follow the steps of your algorithm for it. If your algorithm gives you the right answer, then you are ready to move on. If not, you should go back and fix it first. Now that you have devised an algorithm to solve the problem, you're ready to translate that algorithm into code. This step is where the syntax of a specific programming language comes into play. You need to write down your steps in the syntax of that language. Once you've written your code, you want to be sure that it works correctly. So you run test cases on it. Running a test case involves executing the code on a particular input and checking if it produced the right answer. The more test cases your code passes, the more confident you can be that it is correct. However, no amount of testing can guarantee that the code is right. When your program fails a test case, you know something is wrong. And when that happens, it's time to debug your program. You can watch a review video about debugging if you need more information, but at a high level, you will apply the scientific method to understand what is wrong with your program and determine how to fix it. Once you have identified the problem using the scientific method, you will need to revisit a previous step to fix it. If the problem is in the algorithm you designed, you will want to go back to step 3 and rethink your algorithm. If your algorithm is correct, but you implemented it incorrectly in code, you will want to return to step 5 to fix your code. Now you have learned the 7-step approach to solving a programming problem. In the next video, we will work through an example of the process. This process can guide you through programming problems you need to solve not only throughout the rest of this course, but whenever you need to solve a difficult problem. Thank you.
Hi. In this video, we're going to walk through an example of using our 7-step process to solve a programming problem. In particular, the problem we're going to work on is, given a shape, find its perimeter. Step 1 is to work an instance of the problem yourself. That means you'll need to draw a shape and find its perimeter. We'll need a little domain knowledge here for this problem. Specifically, what is the perimeter of a shape? If you don't recall, the perimeter is the sum of the lengths of all the sides of the shape. We'll need to know that a shape is defined by its points, and the points are listed in order as they appear around the perimeter. First, we'll draw a coordinate grid so we can draw our shape precisely and carefully. Then, we'll draw a shape on that grid. We're noting the coordinates of each point in the shape as we draw it. This will allow us to easily do math on them to compute the lengths of the edges of our shape. Once we have the shape, we can start finding its perimeter. This left edge has length 4, and this bottom edge has length 5. So we can add them together and get 9, the running total of our perimeter. The next edge is the diagonal, so we'll need to do a little bit of math. The difference in the x's is 3, and the difference in the y's is 4. The square root of 3 squared plus 4 squared, 9 plus 16 or 25, is 5. That's the length of this edge. We can then add 9 plus 5 so that our running total is 14. Now we see that the last edge has length 2. We add 2 to 14 to get 16. So 16 is our answer for this particular instance of the perimeter problem. Now you're ready for step 2. Writing down specifically what we just did. First, we found the distance from the first point to the second point, which was 4. Then we took the second point to the third point, which was 5. Then we added 4 plus 5 to get our running total of 9. Next, we found the distance from the third point to the fourth point, which was 5, and added 9 plus 5, so our running total is 14. Then we found the distance from the fourth point back to the first point, which is 2, and we added 14 plus 2 to get 16. Last, we said that 16 was our answer. So we can write down the steps to solve this particular instance of the problem, as you can see here. Now we're ready to move on to step 3, where we're going to find the patterns and generalize to find the perimeter of any shape, not just the one we just saw. One thing you might notice is that we're doing almost the same thing repeatedly. When we generalize, we want to look for similar steps and express them as repetition. To do this, we'll need to make them match up exactly, which we might do here by starting out by adding 0 plus 4 to get 4. Why does this seem like a good way to make these match up? We'll keep adding the previous result to our running total of all the lengths, so it makes sense to start with 0 for our running total and add our current result to it. The next thing we might do in generalizing this algorithm is give this quantity a name. It won't always have these values, so we should name the quantity and refer to it by that name. We'll call it curdist, since it's the current distance. When we name this quantity curdist, we'll also want to change all the places we use that value when we computed it to reflect the name that we just chose. This gives us an algorithm that looks like this. Next, we should give this quantity a name. Here, total perimeter makes sense, or total perim, as this quantity is the total perimeter of the shape that we're calculating as we go through the steps. Again, when we name the quantity, we'll need to replace the places we use that value using the name we just gave it, total perim. This gives us an algorithm that looks like this. Let's stop and look at this algorithm for a second. Does anything strike you as maybe just a little bit odd? What about this place that we used 0? It isn't a previous value that we computed, but why did we put this line in to begin with? We wanted all the steps to repeat exactly, but now they look different. Can we make them look the same? Sure. We can make total perim start at 0 before we begin the repetitive steps. Then we can just update total perim in our first step. Now these steps form a repetitive pattern. They're the same except for which particular points they're working with. The first point in each of the repetition counts through the points of the shape in the order in which they appear. That's great. We like it when we can iterate over a sequence because we can ultimately express this in code with a for each loop. But this second point in each repetition is a bit more problematic. We'd have to have a way to get to the point after the current one. Now there are ways that we could set up our shapes interface or API to iterate over the points and ask for the next one too. But let's do something very clever. Let's reorder the steps so that we do the distance from the fourth point to the first point first. That is, let us write the steps in this order. First, is it okay to do this? When we want to reorder things, we have to think about it and be very careful. Here, the reordering is totally fine. It's totally fine since addition is commutative. It doesn't matter what order we do the addition in. Second, why is it useful? Well, now we're going through the points in order, giving us a natural for each repetition. But the other point, which does not lend itself to the for each repetition, is the one we just used. That means we can simply remember the previous point in a variable and use it with the next point. We express this idea by updating our algorithm to look like this. Notice how we update prev point to be the point we just finished with, before moving on to the next point. Then we make use of that point in the next set of steps. But what about this point? We can use the same idea we saw earlier when we initialized total perim to 0. Start prev point out with the value we want before we begin repeating the steps. But will it always be the fourth point? No. It just happens that we had 4 points here, but in general, we'll want to start prev point as the last point in our shape. Okay, great. Now we have nice repetitive steps where the only difference is the point we're working on, and those go in order through the points in the shape. So we can express all these steps in the colored boxes that you see here as a repetition for each point of the steps. This gives us a nice general algorithm for finding the perimeter of any shape. Later, we'll translate this into code. Hi, we've developed an algorithm to find the perimeter of any shape. But are we ready to turn this algorithm into code? Well, we could, but we'd like to be confident that it's right before we do that. After all, there were a lot we had to do to generalize our steps, and it's entirely possible that we made a mistake. Or perhaps we just didn't think through all the special cases. So before we turn this into code, we should test it out. To test the algorithm, we need a different instance of the problem, something other than what we used to make the algorithm. In fact, it's good if our test instance is pretty different from the one we used to make the algorithm. Here, we've shown a triangle instead of the four-sided trapezoid we used when we developed the algorithm. Before we go any further, take a second to figure out what the right answer is. What is the perimeter of this shape? When we finish, you'll want to check if the answer to our simulated algorithm is correct. And to do that, you'll need to know the right answer. Now, we'll execute the algorithm by hand for this particular input. As we test the algorithm, notice the similarities between the code and English. We're going to execute this English algorithm by hand, just as we executed code by hand. They both work pretty much the same way, and that's not a coincidence. When you turn this algorithm into code, you want to write down code that has the same semantics as the English, the same meaning. The code should transform the program state in the same way that the English transforms this diagram. So we'll start with total parim and set it to 0, and prev point being the last point in the shape. But what is the last point? We'll say the points in this shape start at the top and go counterclockwise. So this point in the lower right-hand corner is the last one, and we'll initialize prev point to be that point. We'll note briefly that if this were actual Java objects, prev point might be an arrow pointing at an object, but we're going to just write down the coordinates here to keep the diagram simple and legible. Next, we're going to do the steps for each point. So we need to start at the first point, which is this one at the top of the diagram, and that will be the initial value of curve point as we enter the for each repetition. Then we'll find the distance between these 2 points, which is 10, and we'll update total parim to be 10, 0 plus 10. And then we'll update prev point to be curve point. Now we're at the end of our for each repetition. So we'll update curve point to be the next point in the shape, which is -3, -4. When we update curve point, we go back to repeat these steps. We repeat the steps again, finding the distance between those 2 points, which is 8. And then we update total perimeter to be 10 plus 8, or 18. And then we update prev point to be the current point. Then we go back to the top of our loop, updating curve point. We repeat these steps for the last point in our shape, after which we've gone through all the points. So we skip to the steps after our repetition. Here, we can say that total parim is our answer. Total parim is 24. Is that the answer you came up with earlier? Yes, that is the perimeter of this shape. The fact that our algorithm came up with the right answer here gives us more confidence that we generalized correctly. We're done executing the algorithm by hand, and we have some great confidence that it's correct. So we're ready to turn the algorithm into code.
All right, now you've developed the algorithm to find the perimeter of a shape, and we want to turn it into Java code. You've seen a lot of Java code as we've talked about the syntax and semantics, and so what we're going to do is step by step go through and take the algorithm that we wrote and turn it into code that has semantics that match what we wanted our algorithm to do. So here I have a class called perimeter runner. It's going to have the method getPerimeter, which takes a shape and returns a double. It's got some other code in here, so it has a main that we can run, which will make an instance of this class and call testPerimeter, which will use file resource to read from a file and create a shape, and call the parameter and then print that out. We're going to go through and translate this to code, and I've written our algorithm here as comments, which are things for people that the compiler will ignore. So the first thing we say is start with total param equals 0. So this sounds like we needed a variable. We called it total param. We're going to set it equal to 0. We need to think about what type we want. Since we set it equals 0, we might want an int. But if we think a little more carefully, we might realize we want a double since we're working with floating point numbers that might have fractions. So double total param equals 0. And if we'd written this as int, we hopefully would find that out in testing when we come up with answers that should have fractions and we don't have them. Then we say start with previous point equals the last point. So we need another variable previous point. What type of variable is this? Well, this is going to be a point. And it's going to be the last point. We meant in S, even though we didn't write that down. So we'll call get last point. How do I know that was there? I looked at the documentation for shape before I started doing this video and saw that it has a get last point method. Then we say for each point, which we wanted to call cur point in the shape. So this sounds like a for each loop. Each point, cur point, in the shape dot get points, which is going to give us all of the points. We want to do these steps. And I'm going to go ahead and put them in curly braces. We want to find the distance from previous point to the current point and name it cur distance. So anytime we want to name a quantity, we want a variable. And so that's going to be the distance from prev point to cur point. Then we're going to update total param to be total param plus current distance. And then we're going to update previous point to be current point. Last, we said total param is my answer. Whenever we know our answer, we're going to return that because that's how we give our answer back to whoever called us. So now that I've written this code, I'm going to come up here and I'm going to click compile. And it says cannot find symbol variable shape. It's because my shape was called S. And now it says class compiled with no syntax errors. So now I'm going to shrink this window down a little bit smaller. I'm going to come over here and I'm going to do main. Even though that's how we run programs outside of BlueJ, if we've written a main, we can do that. We're going to give it no arguments, so I'm just going to click OK. And it's going to ask me what input file has the points for this shape. So each of these files has some points. So for example, example 1 has -1, 3, -1, -1, 4, -1, 1, 3, which is what we used when we developed our algorithm. So that's a good first check. Make sure we get the answer we expected. And that gives us 16, which you may recall is what we came up with when we worked this example ourselves. Of course, using that might be bad because if we made a mistake, we wouldn't necessarily catch it since we've already used those values in developing this, so we might want another one. And so this says that this other shape with points of -3, 4, -3, -4, and 3, -4 has a parameter of 24. If you work that out yourself, you'll find that that's the right answer. And so we become more and more confident that this code that we just wrote is correct. So that's how you turn your algorithm into code. You go through step by step, take each step, write down the code that corresponds to what you wrote.
Hi, I'm Dr. Raluca Gordon. I'm a professor in the Duke Center for Genomic and Computational Biology and in the Department of Biostatistics and Bioinformatics. My work is strongly based on designing and using computational algorithms, programs, and tools, and I want to tell you just a little bit about that. But first, I'd like you to think about the word strings. What does an orchestra conductor think about when she hears the word strings? What does a sailor think about the word strings? What does a pianist think about the word strings? Well, I'm a genome scientist, so I will tell you what I think when I hear the word strings, and that is genomic strings. The genome of an organism stores all the genetic information necessary to build and maintain that organism. This genetic information is stored as a long list or string over the 4-letter alphabet A, T, C, and G. These 4 characters correspond to the 4 DNA bases: adenine, thymine, cytosine, and guanine. The sheer size of the genome makes it difficult, if not impossible, to analyze by hand. The human genome, for example, contains 3 billion characters. That is 1,000,000 times more than the characters shown here. Thus, finding any information in the genome requires computational approaches. In addition, the genome is complex and contains different types of information. Computational approaches are needed to find information, including genes, as you can see here. Finding genes requires more than simply looking for the tags or codons that identify the start and end of a gene. In addition to genes, such as the one shown here in red, we also need to look for regulatory elements, as shown here. We do this with computational tools and techniques. These regulatory elements are shown here as simple letters representing nucleotides. But it's important to remember that these are actually bound by proteins called transcription factors, which help turn genes on and off. My research is focused on identifying such regulatory elements in the human genome using various computational approaches. You will do similar things in this course, and this will prepare you to become a computer scientist or a genome scientist, depending on what your preferences are.
Hi, and welcome to this lesson on finding information and patterns in data, which is a very general topic that we will make concrete in working with Java strings. Strings are sequences of letters, digits, punctuation, any character that you might type, for example. Why will you learn about strings? You've learned previously that everything is a number. That's true, as you can see here, where I've captured the beginning of 3 different files. These files might be stored in memory, on a flash drive, or on your computer's hard drive. The first file was a video, a file with a .mp4 suffix. The second file was an image, a file with a .png suffix. And the third file was a plain text file with a .txt suffix. Can you tell which group of bits of zeros and ones goes with which file by simply looking at the zeros and ones? Some people may be able to do that, but most cannot. Although everything stored on a computer is a number, information stored on a computer is often readable. We use strings to store data so that we can read it and so that we can write programs to read the data and process it. Here are parts of 3 data files where the data are stored as strings. It's important that the data is readable by you, not just by the computer, although we could write programs even if everything was only a number. It will be easier to write programs to find patterns, knowledge, and information and data when the data is stored as strings. The first part of a file is genomic data stored in what's called FASTA format. You'll write programs in this lesson to find proteins and genes in genomic data. The second part of a file is from a web page. You'll write programs to find links and other information in a web page, doing at a small scale what search engines like Google do in ranking pages to be found by those doing web searches. The third part of a file is data from a CSV file, or Crime in Sacramento, California in 2008. A CSV file is a file in a special format. The CSV means comma separated values. You'll write code in a later lesson to process CSV files. We have several goals for you to learn as part of this lesson. You'll learn about the Java string class. You'll learn many details, how to write programs with the string class and how that's most often done. You'll learn common string functions and how to read documentation to find out more about strings. You'll learn about Java types and operators. Here you'll learn more about Java's numeric types and operators on those types, which for you will be int or integer and double or a floating point number. You'll learn about programming to find patterns in data by searching for specific parts of a string. You'll repeat searches to find information and patterns like all the links on a web page or all the genes in a strand of DNA. Let's get started solving problems. Thank you. Hello and welcome back. You are going to be working with strings that represent DNA, solving problems like searching for genes in them. This problem is a great one to learn on because even though we're going to start with a greatly simplified version of it, it's an important problem with real-world applications. Of course, the lessons you will learn about working with strings and programming in general will help you far beyond this problem domain. Whatever sorts of problems you want to solve, strings are likely to come up in them in one way or another. HTML, email, or really anything that is text that is represented as a string. You are also going to learn some other important lessons as you work on these problems, like how to do math in Java. Of course, math is also ubiquitous in programming since everything is a number. And perhaps most importantly, you will get more practice developing and implementing algorithms with the 7 steps. Before we dive into DNA-related problems, we need to give you a bit of domain knowledge, some terms and concepts related to working with DNA. Here is a string that could represent some piece of DNA. You will see that it's made up of 4 letters, A, T, C, and G. Each of these represents one nucleotide, which are the basic building blocks of DNA. 3 nucleotides together make a codon, which each describe one amino acid. The ATG codon shown here is special in that it indicates the start of a gene. Accordingly, it's called the start codon. And the TAA codon is also special in that it indicates the end of a gene, so it's called the stop codon. There are a couple other stop codons, but for now, we're only going to think about TAA. Everything between and including these 2 codons makes up one gene. The first problem you're going to work on is finding a gene in a string which represents DNA. That is, you want to write a program which takes a string like this one and gives you all the text between it and including the start codon ATG and the stop codon TAA. You're going to start with a greatly simplified version of this problem, just finding those letters and all the text between them. You will not worry about the fact that real genes must be multiples of 3 in length because they're made up of codons, or that there are some other stop codons, or a few other complexities to start with. As you master more string and algorithm concepts, you'll add features to your program, making it more realistic with each step. As always, the first thing you want to do is work on an instance of the problem yourself. Let's take this DNA sequence and find the first gene in it. Let's find the start codon. Aha, there it is. Now let's start looking after it to find the stop codon. And we find it right here. That means that we want to take all this text representing the nucleotides in this region as our answer, the gene that we found. Now that we have worked an example, we should write down what we just did. First, I found the first occurrence of ATG. Then I started looking after the ATG for TAA. Last, I took all the letters between and including them as my answer, ATG, ATT, TTC, etc., all the way to TAA. Okay, now that we wrote down what we did for that specific problem, we want to generalize it. Why did we look for ATG? We always want to look for it. That's the start codon. What about TAA after ATG? We always want to do that too. That is the stop codon. And taking all the letters between and including them, we always want to do that too. The only thing that isn't really general here is the specific string we wrote down as our answer, which was more of a descriptive note to ourselves than anything else. Now that we have a general algorithm, we'd like to turn it into code, but we need to learn some new Java concepts first. How do we find ATG in a string? For that matter, how do we even represent or talk about the position of something in a string? And how would we get all the letters in a particular range in a string? You'll learn about these concepts, then you'll be ready to turn this algorithm into code. Thank you.
To move forward implementing a gene-finding program, we will explore a couple of important string topics in this video. The first of them is how we can represent the position of something in a string. To answer this question, we return to the recurring concept that everything is a number. That is, we will give each position in the string a numeric index. Notice that these numbers start at 0 in the first position, not 1. This may seem a bit odd, since we usually start counting from 1, not 0. However, many programming languages start numbering sequences of things, such as strings, from 0 because it makes some tasks easier, as we shall see later. These numbers, which describe the positions in the string, are called indices or indexes. Either word is an okay plural of index. For example, if I wanted to talk about this E, I might say the letter at index 3 is E. We have now answered the first question. We can represent the position with a number, and we can talk about the index in the string where we find the ATG. Now it is time to answer the second question. How could we get all the letters in a particular range? Which we could now be a bit more precise and say between two particular indices. One option would be for you to write your own algorithm to do this. However, you can also use a built-in method of the string class. Whenever there is a built-in method to accomplish a particular task, it is better to use it than write your own. Not only does it save you work, but the built-in method has already been heavily tested by expert programmers, so you can be very confident that it works correctly. For this particular task, you want to use the built-in substring method. However, before we show you how to do that, let's take this example string and make it an actual Java string, assigned to a variable. Here we have a variable declared with the name s, of type string, and an equal sign to make an assignment statement, and a semicolon at the end of the line to end the statement. However, this isn't quite correct yet. We also need to put the string literal in quotation marks, as shown here. If we did not put these and just wrote the word, Java would think Duke programming was the name of a variable and give us an error that is undefined. By putting the text in quotation marks, Java knows that we want a string with that literal text. So now we have a valid statement which makes the variable s be the string Duke programming. Next, you can see an example of using the substring method. Here we declare another variable of type string called x and assign it to the result of s.substring 4, 7. What do these numbers mean, and what does this method call do? The first number specifies the index in s from which we want to start making our substring. The letter at this index will be included in the resulting string. The second number specifies the index in s where we want to stop making our substring. The letter in this index will be excluded from the resulting string. The method will stop right before it gets to that letter. This may seem odd. Why would you want to specify the index after where you want to stop? There are a variety of reasons why this method and many others are designed this way. But one nice reason is that the length of the resulting string will be the difference between the two numbers. 7 minus 4 is 3. So we will get a 3-letter string as our answer. In particular, you will end up with this 3-letter string made up of the letters from the indices 4, 5, and 6 of s. So x will be the string PRO. While you are learning about this built-in method of string, let's take a moment to talk about a few other useful methods and what they do. You just saw substring and learned how it gives you the letters in a particular range of indices. Another useful method is .length, which tells you how many characters are in the string. The string s has length 15. Notice that for a string of length 15, the valid indices are 0 through 14. If you try to access an index outside of this range, your program will have an error with a string out of bounds exception. Another really useful method is .indexOf. You pass this method another string and it tries to find the first occurrence of that string within the string you called the method on. For example, here we have asked the indexOf method to find the string program within the string s. You can see that the first occurrence of program is right here since it starts at index 4. That is the value that the method call would return. Here's another call to indexOf, s.indexOfg. Can you figure out what this would return? This will result in 7, since the first occurrence of the string g starts at index 7. If you call .indexOf on a string that is not found, such as .indexOf f, it returns -1. You can also give .indexOf a second parameter, specifying the index to start searching from. Here we have passed 8 as the second parameter, so the .indexOf method will ignore characters in the indices 0 to 7 as it searches for g. It will then find this g, which is the first one when you start looking from index 8. So this method call evaluates to 14. Another useful method is .startsWith, which tells you if a string starts with another string. Here you can see that s starts with Duke, so this method call evaluates to true. Likewise, .endsWith checks to see if a string ends with another string. S does not end with king, so this method call evaluates to false. Wow, that was a lot of methods and a bunch of information. How would you know all of this without us telling you about every method in the string class? And should you be memorizing all of these details? Of course not. Programming is not about memorization. Although, as you program a lot, methods that you use commonly will naturally become familiar. Instead, you should learn how to make use of the language documentation, which describes all of the built-in classes and their methods. If you search the internet for Java string, your first result will probably be something from docs.oracle.com. Oracle is the company that makes Java, and docs.oracle.com is the website where they host the language documentation. If you click on this link, you will end up with a page that tells you all about the string class. If you scroll down a bit, you will find a rather long list of all the built-in methods in string. Here are a few of them, including a few that you have just learned about, .indexOf and .length. These entries give a brief description of the methods, and if you click on one of the method names, you will get a more detailed description of what that method does. There's also a documentation page on the course site at DukeLearnToProgram.com. That page has simplified documentation of some important methods for quick reference. Great! Now you not only know about indices in strings and some useful built-in methods, but also how to learn about other methods when you need them.
Hi, we're going to find a gene in a DNA strand. We're going to do a very simple algorithm in order to find our gene. So I've started some code here. We have an algorithm method called findGeneSimple, and we haven't done much with it yet, but what I've also done down here is I've written a couple of DNA strands that we will use to test the code that we write. So you can see here we have string DNA. We're going to print our DNA strand. We're going to call findGeneSimple, and then print out our gene, and then I just have done this with 4 different strands of DNA. So let's write the code now. So I've started by just saying the resulting gene is just going to be called a variable called result, and I've set it to null, the null string. And if you remember from the video, we are going to look for the start codon in the strand of DNA. And the start codon is ATG, the string ATG. So we can use the new string functions that we learned about. So I'm going to start by creating a variable that will hold the index position of the start codon. So we'll call it start index. And then we are going to look in the strand of DNA, and we'll use the index of function to look for ATG. And the index of function is going to go through the string, and it's going to stop when it finds ATG, and it's going to return the index location of where it starts. So that'll be the starting position of our gene. We also have to look for the stop codon, and that is TAA. So we're going to create a variable for that called stop index for the position of where the stop codon is. Again, we will look in our DNA strand. DNA, we'll use index of. But if you just look for TAA, it will start at the beginning of the string. And we want to look for the stop codon after the start codon. So we know where the start codon is. It's in the variable start index. And we want to start looking past that. So you can add a second parameter to the index of function. And so we will add that and say start looking where ATG is, which is start index, plus 3, which is the length of ATG. So now we have the start index and the stop index of where start index of ATG and the stop index of TAA, and now we want the strand that includes those two and everything in between it. So I'm going to call that our result. Again, we'll use a string function. So we'll use the string function called substring. And the way substring works is you have to say, I want a piece of a string and I want to start. Where do we want to start? We want to start where ATG is. So we'll start at the start index. And then the rest of our gene is going to be everything past ATG up until TAA, which is at the stop index. But we also want to include TAA, so we'll add 3. So that means take our substring from where ATG starts, go all the way to the stop index plus 3, which is the first character after TAA. And the way substring works is it says start at the first start index and then go all the way up to, but not including the second parameter. And then let's compile this and see if it works. Okay, so it compiles fine. So let's go over here and we'll create a new find gene. And now we'll run our test method that we wrote. And there it is. So we can see here's the first DNA strand, and you look for ATG, there it is. And then look for TAA, and there's the first TAA that's after it. And you can see there's the gene that we found right here. And then the next example, here's ATG. We look for TAA all the way here, and you can see here that's the gene we found. Here's the third example, ATG all the way to TAA, and you can see we got a big gene there. And then here's the last example, ATG, TAA. So that works good too. All right, but what happens if ATG is not there? Or what happens if TAA is not there? So let's look at our example here, and let's change one of our strings. Let's change this string. We'll just save this one. And let's change it to a string that does not have ATG in it. Let's see what happens if we run that example. So we're going to come back over here. And we'll run our test find, and we got an error down here. You can see it says string index out of bounds exception, -1. String index out of range. what happened? Let's go look at our code. So we looked for ATG and we didn't find it. And what the index of function does, if it doesn't find the string you're looking for, it returns -1. So start index has the value -1. And then we're trying to build a string starting at -1, and -1 doesn't exist. So we got an error. So what are we going to do? We need to fix this code. So let's check right after we ask for ATG. Let's put an if statement in there to check to make sure that ATG was there. So we can ask if start index is equal to -1. That means there is no ATG. In that case, we need to, there is no gene. There is no gene if there's no ATG, there's no start. So what we'll do is we'll just return the empty string. So if we compile this now, and if we run it, get rid of this. So we'll create find gene, and then we'll run test find, and it ran, but there's no gene here. And that's because there's no ATG. Let's try another example. We'll change our code again to give another example. Let's just change this one here. Let's create a string where we have ATG, but we don't have TAA. So we have the start codon, but not the stop codon. So I'll create a string CGATG, GTTTAAA, AGT. So there's no, oh, there is, let's get rid of it. There we go. So now we have ATG right here, and to the right of it there is no TAA. So let's compile, and we'll run it. And you can see there it's not there. There's no gene for this second one because ATG, but there's no TAA. All right, so just like we put a check for if there's no ATG, we should do the same for if there's no stop codon, so no TAA. So let's add that code too. We would add it right after we get the value for stop codon. So right here we can check and see if stop, if the stop index equals -1, at that point we know there's no stop codon, and so there's no gene. And so we can again just return the empty string. Return empty string. So that's just a safe way. If there's no start codon or no stop codon, let's add a comment here. This is the case for no TAA. We'll compile our code, and we'll just double check and make sure that works. So it compiles, and we'll run it. And now we have our first string is good, we find a gene. Our second string, there is no gene, we have an ATG, but we don't have a TAA. This string looks good. This string has no ATG, and it actually does have a TAA, but that doesn't matter because it has no ATG. And so this gene, there is no gene for that one either. So anyway, that is the way to find a simple gene in a strand of DNA. We look for the start codon, and then if there's a start codon, we look past it for a stop codon. And if we find both of those, then we can return the start codon, the stop codon, and everything in between it as the gene. Thank you. All right, now you have an implementation of the rather oversimplified version of this program. It just looks for ATG and then TAA and gives back everything in between. But real genes have to be a multiple of 3 in length, since they're made of codons, each of which is 3 nucleotides long. For example, this string is a valid gene. You can see here how it can be divided into codons starting with ATG and ending with TAA. However, this string is not valid. Even though it has ATG and it has TAA, when we look between them, we don't find a valid sequence of codons. Now, let's make our algorithm a little bit more realistic. You will fix this aspect of your algorithm. It will still be a simplification, but a bit more realistic. At this point, it's really good to note that starting with the simple version and adding features is not only a useful technique for you as you learn new concepts, it lets us introduce a few concepts at a time, but also important when writing real, large, complex problems. Okay, so you just saw 2 examples of DNA strings. One that has a valid gene and one that does not. But how can you tell in general what is the change you need to make to your algorithm? It might be useful to show the indices, as we have shown here, and highlight the location of the start and stop codons. Do you see how to algorithmically tell the difference? If not, that's fine. It can be hard to spot patterns, but you will get better at it with practice. One great technique to find patterns is to make a table. You might remember that we did this in some of our examples. We can then add more examples to our table, as I'm showing here, to help us see the pattern. Some with yes answers and some with no answers. Maybe you see the pattern now, or maybe it is still hard to see. What can you do if the pattern still isn't clear? Maybe adding more rows will help, or maybe not. Instead, we might start exploring the relationships between the items in the table. Here we have added another column for the difference in the index of the stop codon and the index of the start codon. The ones that have yes answers have differences of 6 and 12, and the ones that have no answers have differences of 4 and 11. What do 12 and 6 have in common that 11 and 4 do not? We might be able to think of a lot of things. 6 and 12 are both multiples of 6, but that doesn't make sense in the context of this problem. If we did more examples, we could find ones with yes answers that have 3 or 9 or 15. However, 6 and 12, as well as 3, 9, and 15, are all multiples of 3. This relationship does make sense, as we know that the length must be a multiple of 3. Now that you know the relationship you know that you want to look for, you need to do some math in Java. You need a way to ask if the difference between 2 numbers is a multiple of 3. If you took course 1 with us, you might remember the mod operator, which gives you the remainder when you do division. X mod y, written x%y, means divide x by y, but give me the remainder, not the quotient. This can help you with the problem at hand, since a number that is a multiple of 3 has a remainder of 0 when divided by 3. That is, if x mod 3 is equal to 0, then x is a multiple of 3. You can use other mathematical operators in Java. Plus, minus, times, divide, they're all valid. You can also use equals equals to see if 2 numbers are the same, not equals to see if they're different, and less than or equals, greater than or equals to check for inequalities. You can also combine simpler expressions into more complex expressions. This expression checks if a minus b mod 3 is equal to 0. It is evaluated by first evaluating a minus b, then taking that result and doing mod 3 on it. Then finally taking that result and checking if it's equal to 0. This is pretty much exactly what you need for the problem at hand, to see if the difference between 2 things is a multiple of 3. While you are learning about math in Java, there are several different types of numbers. Actually, there are some variations on these, but you don't need to worry about that right now. One type of number is int, which represents integer numbers like -2, -1, 0, 1, 2, etc. Ints can't have a fractional part. The other type is double, which represents real numbers, ones with fractional parts like 1.2 or 3.4, 5, 7. Of course, you could also represent 3, which is 3.0 with a double. You only want to use doubles when you need to, since they have some behaviors that can be really confusing to novice programmers. One word of caution about integers, however, is that math on integers always yields integers. So what do you get if you divide 5 by 2? If you're thinking 2.5, remember that you can only get an integer result. So you get 2. What about 100 divided by 3 times 4? You will get 132, since 100 divided by 3 is 33, and 33 times 4 is 132. So what if you do 100 times 4 divided by 3? Seems like you should get the same answer, right? Well, actually, now you get 133. Why? 100 times 4 is 400, and 400 divided by 3 is 133. These sorts of issues should not come up in these courses, but are good to be wary of if you're doing integer division. Another thing to know about math in Java is that it has order of operations, rules like math. In programmer speak, these rules are called precedence and associativity. As with math, A plus B times C means to do B times C first, then add that result to A. What if you have mod? It has the same precedence as division, meaning it takes place at the same place in the order of operations. So A minus B mod 3 means to do B mod 3. Then subtract that result from A. This is why we put parentheses around A minus B earlier when we wanted to do the minus first, then take its result, mod 3. Comparisons for equality happen very late in the order of operations. A plus B equals C minus D means to first do A plus B, then do C minus D, and finally compare the two results to see if they are equal to each other. These rules are typically like they are in math. Multiplication and division come first, then addition and subtraction. Also like math, you can use parentheses to group things so that they come first. If you aren't sure what order things will happen, you can always use parentheses to be explicit and be sure you get what you want. Okay, now that you know about math in Java, it's time to go improve your gene finding algorithm. Thank you. Welcome. I'm excited to work with you as you extend the programming and problem-solving capabilities you've developed for finding genes in a strand of DNA. You'll work on finding genes using a model of stop and start codons that more closely resembles the work done by genome and computational scientists as they work on problems such as personalized medicine and understanding genetic issues with many species. You'll learn about new classes from the edu.duke library, and you'll practice with new programming constructs that will allow you to repeatedly execute program statements until a problem is solved, like finding all genes in DNA or all links on a web page. Let's get started. I hope you have fun. Thank you. Welcome back. In this lesson, you're going to learn a powerful new programming construct, an indefinite loop. You'll also learn about another iterable from the edu.duke library. You've already solved problems using the file resource and URL resource classes from the edu.duke library. Using iterables made it possible to repeatedly access data stored in a file on your computer or via a URL from the World Wide Web. You'll use this concept of repetition to find all the genes in a strand of DNA, a problem that genome scientists do as part of their work, and a problem that models finding all links in a web page, or all the YouTube videos you might want to watch about cats, or dragons, or anything else. The key idea here is that you'll use the algorithm from a previous lesson that found one gene in a strand of DNA, an algorithm you've tested and have confidence in. You'll repeatedly apply this algorithm over the entire strand of DNA to find all genes, not just one. You'll also learn about a new iterable that lets you store intermediate results. Instead of printing all the genes you find, you will be able to store them so that you can look for particular genes after you found strings that could be genes, for example. By storing the results of a gene search or of other kinds of search, you can write separate methods to process the genes rather than including the processing with the finding. This separation of concerns, find genes, process genes, filter any of those genes that have specific characteristics, is a hallmark of good software engineering, writing a method to do one thing rather than doing several things. This separation allows you to reuse code more easily and to develop code more easily. The storage you use will be an iterable you can add to while the program you write is running. To be more concrete, you're going to solve a variation of a problem you solved once before, the problem of finding a gene in a strand of DNA. Genes are found in a strand of DNA at different sites within the DNA. In a previous lesson, you developed code for finding one gene, like the region shown in red here. You found this gene by looking for particular markers called start codons and stop codons. These markers were used to identify the part of a string that could be a gene. You could have used a similar algorithm to find where a link occurs in the HTML text of a web page, looking for ahref rather than ATG, for example. DNA typically carries more than one gene, however, so rather than finding this one gene that's marked in red, you'll use programming techniques to find all the regions in a strand of DNA that could code for a gene, regions that begin with the start codon as shown here, but that also are indicated by one of 3 stop codons. In the next group of lessons, you'll learn many things about Java and programming as you practice solving this gene-finding problem. You'll learn how to repeat a process many times, even when you don't know how many times this is. You'll do this by using a while loop, a new kind of loop that complements the for loop you've used with iterables. You'll learn about the storage resource class from the edu.duke library. Using a storage resource object will allow you to add selected values to the storage and then access them in your code using the standard for loop with iterables you've used before. This storage will also be a preview of future programming techniques you'll learn about in using arrays to store values. You'll also practice with developing if statements and Boolean expressions that use what's called short-circuit evaluation. This will be an important part of the practice and knowledge you'll gain as you move toward becoming a better programmer and problem solver. Thank you. As you have been learning about strings, you have been improving on your algorithm to find genes in DNA. However, let us take a moment to think about what your algorithm will do on this string. It will find the start codon ATG at index 0. Then it will find the stop codon TAA at index 8. It will then check if the distance between them, which is 8, is a multiple of 3. Because 8 is not a multiple of 3, your algorithm will conclude that this is not a valid gene. Between the ATG and TAA, there is one full codon, ATC, and 2/3 of another codon, GC. But if you were to keep looking past this TAA, you would find another TAA at index 15. Now the distance between the ATG and TAA is 15, which is a multiple of 3. So this is a valid gene. The first TAA that we found was not actually a codon, but rather pieces of 2 adjacent codons, the T from GCT and the AA from an AAT. Your next improvement to the gene finding algorithm is to add this functionality, to make the algorithm keep looking until it finds a stop codon that is a multiple of 3 away from the start codon. Having just worked that example, let us now do step 2 of the 7-step process and write down what we just did. The first thing we did was to find the ATG. Then we found the first occurrence of TAA after the ATG, which was right here at index 8. Then we checked if the distance between them was a multiple of 3 or not. In this case, it was not. So we found the next TAA after this first one. The second one is right here at index 15. Then we checked if the distance between this TAA and the start codon was a multiple of 3. It was, so all of the substring from 0 up to 18 was our answer. In this particular set of steps, we checked in 2 places to see if the distance was a multiple of 3. If this works in the general case, you can just implement this algorithm with familiar if-else statements. However, do we always only need to check twice? Let's look at a different DNA string. With this DNA string, we would need to check 3 times. The first 2 TAAs are not a multiple of 3 away from the start codon, but the third one is. Would checking 3 times be enough? Could we have to check 4 times, 5, 10, 50 times? This raises the question of how many times we have to check in general. And the answer is that we cannot pick a particular number of times. Even if you wrote 50 if-else statements, we could come up with a DNA string that has more than 50 TAAs that are not a multiple of 3 away from the start codon before finding a valid one. Instead, we need to write our algorithm so that it repeats the checking however many times it needs to. As you have seen before, repetition in your algorithm will turn into a loop when you translate the algorithm into code. To express your algorithm with repetition, you will need to make the repetitive steps the same and figure out what to loop over. Previously, you have seen for loops, which iterate over the elements in some iterable, such as pixels in an image. Now you're going to learn about a new kind of loop, known as a while loop, which lets you iterate as long as some condition holds. Before we try to generalize these steps by finding repetition, let's be a bit more precise about what we did. We found the first ATG at index 0. For the first TAA, we started looking at index 3 and found it at index 8. We checked if 8 was a multiple of 3. It wasn't. So we started looking at index 9 for the second TAA, and we found it at index 15. We checked if 15 was a multiple of 3. It was, so everything between was our answer. Now, let us take these steps and generalize them. We looked for ATG here. Why was that? We always want to look for ATG because it is the start codon. What about the fact that we found it at index 0? We're not always going to find it at index 0. However, we are going to want to use that information. So let's give that a name. When we turn this into code, what will be a variable that we will assign to this in this line and then use later? In particular, we'll call it start index. What about looking for TAA? We will always want to look for TAA since that is the stop codon. Will we always start at index 3? Probably not. Why did we start at index 3 here? We started there because it was right after the start codon that we found. In the general case, this would be start index plus 3. We won't always find it at index 8 either, so let's give that a name too. We'll call it current index. Let's also be a bit more specific about the distance between them. It is cur index minus start index, which happens in both of these steps. Next, you aren't always going to start looking from index 9. But why do we start at 9 here? If you look back at where we worked the problem and wrote down our steps, we started at 9 because The previous one started at 8. In our generalized algorithm, we named the previous location cur index, so we can start from cur index plus 1. We also should name the location where we found it. Should we give it a new name, such as next index? Or should we just update an existing name, such as cur index? In this case, we want to update cur index since that represents where we have found the most recent TAA. If you did not realize this right away and gave it a different name, you would realize it later on as you try to make the steps uniform so that you can express the repetition. Finally, we'll generalize the last step to just indicate that the text between them is the text from start index to cur index plus 3. Now these steps look repetitive. The repetition may be a bit hard to see since it only happens twice, but if you wrote down the steps for a string with more TAAs that don't work, you would see that you do these steps over and over again. To make this repetitive, let's write it down like this. Notice that steps 4, 5, and 6 are what we will repeat. We've slightly adjusted the steps from before to reflect the choice we were making in step 4 and the two possible outcomes in steps 5 and 6. However, we have left the conditions under which we repeat these steps blank here. How do we know when to stop repeating them? Also, what would you do after you stop repeating this loop? We would stop if we run out of TAAs. If that happened, cur index would be -1, which you know from having learned that you get -1 when you cannot find something in a string. If you were to encounter this case, it would mean that there is no valid gene in the string. So you should give an answer of the empty string. If you did not see this right off, what could you do to figure it out? You should work more examples until you understand the pattern. Now your algorithm is generalized. But you'll need to learn about while loops before you can translate this into code. Thank you.
To implement our improved gene finding algorithm, you need to learn about while loops, the code that generally comes up when you have a step in your algorithm like, as long as some condition is true. You can see an example of a while loop here. Let's look at this example to delve into the syntax and semantics of the while loop. All while loops start out with the keyword while. Then they have some condition, sometimes called a guard, in parentheses. This is the condition that you want to check to see if you should continue doing the loop. Then you have the loop body in curly braces. These are the statements that should be executed each iteration of the loop. Let's walk through this example to understand the semantics of the loop, what it means. For example, let us assume that x was previously declared and initialized to 0 and y was initialized to 7. When execution reaches the while loop, the first thing that happens is Java evaluates the condition, is x less than y? In this particular case, that means is 0 less than 7? 0 is less than 7, so the condition evaluates to true. Since the condition is true, execution will enter the loop body and continue executing statements there. The first statement prints x, which is 0, so we would output the line 0. The second statement sets x to x plus 3, which would update the value of x to be 3. Now execution has reached the end of the loop body. The closed curly brace marks its end. Then execution goes back up to the start of the loop, and we are right back where we started, but the variables have different values. X is 3 instead of 0. We continue following the same rules. Evaluate the condition, 3 is less than 7. The condition is true, so we enter the loop body. Print x, which is 3, and update x to be 6. Now we have reached the end of the loop again, so we go back up to the start of it. And again, follow the same rules. check the condition. It is true, so we enter the loop body. Print x, which is 6, update x to be 9. Now we have reached the end of the loop body again, so we go back to the start. Yet again, we follow the same rules. Now, when we evaluate the condition, something different happens. Is 9 less than 7? No. So the condition is false. Instead of entering the loop body, we go past it. We would then continue executing whatever statements come after the loop. Great! Now you have learned the basics of while loops, their syntax, the grammatical rules for writing them, and their semantics, their meaning. Now you are ready to go code your improved gene-finding algorithm.
Okay, now you've learned about while loops and are ready to turn this algorithm into code, which will search for a TAA which is a multiple of 3 away from the ATG, even if there are other TAAs in between, which are pieces of 2 different codons stuck together. So here's the algorithm that we came up with, and now we're ready to turn it into code. Our first step says to find the first occurrence of ATG and call its index start index. So as you're hopefully becoming familiar with by now, we're going to say int start index equals DNA.index of ATG, because that's going to find us the first index of ATG. Our second step says find the TAA starting from start index plus 3 and call this result cur index. I'm going to say int cur index equals DNA.index of, and we're looking for TAA, and we want to start from start index plus 3. This should also be becoming hopefully familiar to you with index of starting from a position. Now we're going to say as long as cur index is not equal to -1. This is what you've just learned is a while loop. I want to repeat some steps as long as some condition is true. So while cur index is not equal to -1, I want to do these steps here. And I'm going to go ahead and I've indented my steps to match the grouping that was in our algorithm in the slides, and I'm going to just go ahead and put the curly brace here so I won't get confused later. All right, and so what do we want to do as long as cur index is -1? Well, or is not -1. We want to check if cur index minus start index is a multiple of 3. You've seen how to do this previously, where we can subtract cur index minus start index, take that mod 3, and see if it's equal to 0. And we said if so, we want to do one thing, and if not, we want to do another thing. And as you've probably gotten familiar with by now, if not is going to be else. We want to do some other thing in this case. So if so, the text between start index and cur index plus 3 is your answer. So anytime a method knows its answer right away and is done, we're going to return that answer back to whoever called us, which finishes the method and gives back the answer. So we want return, and we want the text between start index and cur index plus 3. What method would you use for this? Hopefully you've become familiar enough with string methods by now that substring is what comes to mind as what you'd want. So DNA.substring, start index, cur index plus 3. And then we said if not, update cur index to the index of the next TAA starting from cur index plus 1. So anytime we want to update a variable, we're going to use an assignment statement, and we can find the next one after that, again using index of to search from a specific position. Index of TAA from cur index plus 1. All right, so that just wrote that step down as it was. My brace is not indented right, so I'm just going to fix that. And then if we get to the end of this loop, if we keep going and cur index is -1, meaning we couldn't find any more TAAs, then our answer is going to be the empty string. All right, so I'm going to save that. I'm going to go over here and I'm going to hit compile. And it says reached end of file while parsing. And oops, I messed up in here somewhere. I'd written some test cases before we started. You'll notice that it's highlighting this curly brace, and if I scroll up, it's highlighting this curly brace. When I wrote these test cases, I forgot to put the curly brace that ends the method. Fix that really quickly. Compile it. And find gene simple. Yeah, I copied and pasted this testing code and changed the method name and didn't change that. So we'll fix a couple careless mistakes there. This is the danger of copying and pasting. You should never do it. Now really it will compile. All right, so I'm going to make one of these. And you'll notice here that I've written a little test method like we've had in the previous ones. Since things are getting a little more complicated with our test cases, I've put these comments here just to mark where the codons are. So this ATG is one codon, and then I've just marked here that this CTG is another codon. And so we can see that this TAA here, for example, is a whole codon, and this TAA here is not a whole codon. So we would expect this method to find this gene right here. And similarly for these other ones. So I'm just going to run this method really quickly. Okay. And for this first one, what did we expect? We expected ATG, CGT, AAT, TAA, ATG, CGT, AAT, TAA. So we got exactly what we wanted. And notice this is where that while loop we wrote just came into use, because this looks like a TAA, but we would have found that it wasn't a multiple of 3, and we would have kept going and found there actually is one later on. And then similarly, we've done this other string, which is a little bit longer, has some more things that look like maybe they're TAAs, but they're not, but it does have a TAA at the end. So we get that really long gene there. And then at the end here, if you look, we don't actually have any TAAs, and we get the empty string, which is what we'd want. So there we go. We've turned this algorithm into code using a while loop, and now it will look for any TAA which is a multiple of 3, even if it's not, even if there's one that's earlier that's not a multiple of 3 away, so that we can get the right answer.
All right. So far you have developed an algorithm that would find the start and stop codons, figure out that the length is a multiple of 3, and return the DNA string for this gene. Now it is time to add another layer of realism and thus complexity. There are actually 3 different stop codons: TAA, TGA, and TAG. So far your algorithm has only looked for TAA, but now it is time to make it look for the first one of any of these 3 stop codons that is a multiple of 3 away from the start codon count. So which one of these stop codons is the one you want? Well, the first TGA is not a multiple of 3 from the start codon, so that isn't the one you want. The second TGA is also not a multiple of 3 from the start, so you don't want that either. That leaves you with TAG and TAA, which are both multiples of 3 away. You want the one that comes first. In this case, the TAG codon at index 12. Okay, so now you know what the problem is. Let's solve it. To do this, let's go back to our algorithm that we have from before. The only thing that was specific to looking for TAA was these 2 occurrences of TAA in steps 3 and 7. Could we start from this algorithm and have most of our work done for us? The best way to do this is to split the problem up. We want to abstract out the part that searches for a stop codon into its own method. We'll call it find stop codon, and it will take the DNA string to search in, the index to start from, and the particular stop codon string, such as TAA, TGA, or TAG, to search for. The algorithm will need a few changes, such as returning the index instead of the text, and looking for any of the 3 stop codons, not just TAA. However, the basic mechanics of the algorithm, searching for a codon that is a multiple of 3 from the start, remain the same. We'll come back to those changes in a minute. For now, we'll just assume we have a find stop codon method that works. Once we have abstracted that out into its own function, we could use it to find the TAA stop codon. And call the method again to find the TAG stop codon. Then one more time to find the TGA stop codon. Note how this corresponds to what we did by hand. We identified the positions of the TAA, TAG, and TGA stop codons. It is a bit different from our example by hand since find stop codon will only give us a position that is a multiple of 3 away from start index, whereas we showed a TGA that was not a multiple of 3 for the purposes of illustration. Now that we have those 3 positions, we want the one that comes first. So we would just need to take the minimum of 3 values, which we will call min index. Finally, our answer is the substring from start index to min index plus 3. Now let's look at what we need to do to the algorithm that we abstracted out into find stop codon. First, these will no longer always be TAA. Instead, they will be the stop codon parameter, which tells us the particular stop codon we are looking for. The other change is that we want to give back the index where we found the stop codon instead of the text between the start and stop codons. Why? Our other algorithm needs these indices to compare to figure out which one to use before it gets the text. Whenever we find a valid stop codon in step 4, we can just give cur index as our answer. However, what should we give back to represent no valid index found in step 6? -1 is often a good choice to indicate no valid index, but let's see how this would work with the way we are using the result of this function. If we were to return -1, we could make it work, but we would have to change this code to do more complex comparisons than just taking the minimum of these 3 values. You'll see this approach later and learn a new concept in the process. But for now, let's make this work such that we can just take the minimum here. Instead, we can return the length of the DNA string, since that is larger than any valid index. Of course, now that we are doing that, we should explicitly check for the case where no valid stop codon was found. If min index is the length of the DNA string, none of the 3 stop codons was found. Okay, great. Now we have an algorithm. Let's go turn this into code. Thank you.
Hi, welcome to another version of Gene Finding. In today's episode, we're going to look for 3 different stop codons. In the previous coding exercises, you've seen code that found 1 stop codon, making sure it was a multiple 3 away from the start codon. In this version of the code that you've already seen described previously, we're going to look for 3 different stop codons. As you can see here, we have TAA, TAG, and TGA. And in order to find each of those, we're going to write another method, a method called find stop codon that we saw outlined before with our 7-step method. Up here, I've got this method, find stop codon, and it has 3 parameters. DNA stir, the string of DNA in which we're searching for a gene, start index, the location at which we're going to begin the search, and stop codon, the specific codon we're going to be looking for. We've got the code from our 7-step process, and what we're going to do here is write the code that goes along with this. You can see here, as we saw in the previous version of code, I'm going to create a variable cur index, and I'm going to make it the location of the first stop codon starting at start index plus 3. So as we've seen before, the way we do that is create an integer variable, cur index, and we write cur index gets the location in DNA stir of the stop codon starting at start index. That's exactly what it says here. Find the stop codon starting from start index plus 3, so I better make sure I'm doing that correctly, and store that value in cur index. Now, as long as cur index is not equal to -1, and as you've already learned, that's a while loop, so we're going to say while cur index is not equal to -1, and when I type the right curly brace, as you see here, I'm going to make sure I put in a left curly brace at the same time, indented the same way. And one thing I can do there to make sure that I've got it right is to compile my program. So I'm compiling it, and you can see I've got no syntax errors. So I know I'm on shape. Now, as long as cur index is not equal to -1, so I've just coded that, check to see if cur index minus start index is a multiple of 3. I'm going to store that difference. I'm going to say int diff gets cur index minus start index. Now you don't need a new variable for that. As you saw in the previous video, you can just say if cur index minus start index mod 3 is equal to 0. But this is sometimes easier conceptually to say if diff mod 3 is equal to 0. That means, and you can see I've already got my curly braces in there, return cur index because it's my answer. So I'm just going to say return cur index. That's what it says here. Check if cur index minus start index is a multiple of 3, and if so, cur index is the answer, return it. So I've got those two things taken care of. And it says, if not, update cur index. So if not, that would be else. And if you think carefully, you might see that although I don't need the else because I've already returned, but it's probably easier to write it that way in terms of thinking about it. It says, update cur index, looking for stop codon again, starting from cur index plus 1. So you can see up there how I looked for it. So I'm going to do the same thing. Cur index gets DNA stir dot index of. I'm still looking for stop codon. And remember, that's a parameter to this method. And I'm starting, according to our comments, at cur index plus 1. So cur index plus 1. And if we exit the loop, we didn't find the stop codon, so we return DNA stir.length. You can see here that the loop is going to continue while cur index is not equal to -1. If it is equal to -1, we've exhausted the string, the DNA strand in which we're searching, and so it says return DNA stir.length. As we'll see later, when we write this code, that's to ensure that when we find the minimum value, that our code works properly. So I'm going to make sure that my method looks right, find the stop codon, and I started at index plus 3, so that's the last comment I have. I'm going to get rid of that comment now. So I've stored in cur index the location of stop codon. While that's not -1, if it's a multiple of 3, I'm done. And if it's not, I need to keep searching. My class compiles, but just compiling doesn't indicate at all that I'm done. I've written some test code down here, test find stop. And you can see, as you saw in the previous coding video, I've created a strand of DNA, and I'm going to look for TAA, which is one of the stop codons. And I've got it in 2 different places. When I run the method, you'll see what it does, and then I'll describe how that testing works. So here's my workbench. I'm going to right-click on this and make a new object. It comes in the object workbench. I'm going to right-click again, and I'm going to run test find stop. And you can see it printed tests finished. That means all the tests worked correctly, because if there was an error, my print statements would have indicated that. Let's look at that testing code so you can see how I did that. In testing find stop, the first thing I did was look for the stop codon TAA starting at index 0. And you can see here I've got the indices printed above the string. So TAA here is at index 9. 9 minus 0 is in fact a multiple of 3. So it should have returned 9, that it found TAA. And if it wasn't 9, I got an error. To see how it might work if it returned the wrong thing, suppose I said if dex is not equal to 10. Now that would be a mistake because we know it returns 9 and it's supposed to return 9. You'll see in this case when I run it that it will print something. Right-click to create the object, right-click to invoke the find stops, and you can see error on 9. Now that wasn't an error because I knew I was supposed to get 9. All these tests print something if there was an error. And if there's no error, they don't print anything. My last print statement prints when the tests are finished. So what we have now is this method find stop codon written and tested, and we're ready to move on to the next method, which was the same method that you saw before for finding just a single stop codon, and now we're going to find any occurrence of a stop codon, any occurrence of 3 different stop codons. We're going to find TAA or TAG or TGA. This will be a very straightforward use of the abstract method find stop codon that I've already done, so I'll do this very quickly. Find the first occurrence of ATG, the start codon, and store that in start index. So int start index gets DNA.index of ATG. If start index is -1, I'm done. There's no start codon, so I can't find a gene. So if start index equals -1, return -1. I did not, return the empty string. That's what it says right here. And this method returns a string, so I'm returning the empty string. Now I'm going to store in TAA index the result of this method call. So I'm just going to copy and paste this method call, even though, as you've learned, copy and paste does not always work as you intended. So store in TAA index that method call. And then I'm going to store in TAG index the same thing, but it says use TAG. And then I'm going to store in TGA index that call with TGA. I'm looking to make sure that my copy and pastes worked properly, because copy and paste can sometimes be your friend, but sometimes it can get you into trouble. So I've done that. I've used TAA index, TAG index, and TGA index. I've got all those variables. The next comment says store in min index, the smallest of these 3 values. So I have to find the smallest of all these values. And one way to find the smallest value is to use the min function in the math library. So I can say int min index gets math.min of TAA index and TAG index. That's the smallest of these 2. Maybe I call that temp. And then I'll store in min index the minimum of temp, which is the first 2, and the last one, which is TGA index. Let me go over that again. I've found the minimum of TAA index and TAG index. That's these 2. And then I found the minimum of that value, which is the smallest of 2, and my last index, TGA index. And it says if this is DNA.length, I return the empty string. So if min index is equal to DNA.length, return the empty string. Otherwise, the answer is the text from start index to min index plus 3. And as you saw before, that uses the DNA substring method from start index to min index plus 3. I'm going to make sure I've got that right. Compile. Cannot find symbol min index. And that's because I spelled that wrong there. Now it compiled and there are no syntax errors. Just compiling doesn't mean my code works. I really need to test it. So we'll leave it to you to test this. Just as I found a test method here, you could write a test method to test these. It'd be very similar to the one that you saw in the previous video, but I could use TAA and TAG and TGA. Once that test method is done, I'll be confident that my method worked correctly. One final thing, this use of math.min to store in temp and to store in min index, just to let you see, it would be possible to do that on one line. I could say math.min of TAA index and math.min of TAG index and TGA index. It's possible to chain the occurrences of min index together like that. I'll leave that as a comment so you can look at it and think about it. And that's it for coding with DNA and 3 different stop codons. Have fun. Okay, now you have an algorithm which works with any of the 3 stop codons. However, let's explore how you could make this code work if we decided to have find stop codon return -1 when there's no valid stop codon rather than the length of the string. Note that this is a perfectly valid design choice and mirrors what the .indexOf method does, but we need to learn a new concept to make it work with our code. You'd want to change line 6 of the gene finding algorithm to reflect this choice. You cannot just take the minimum, since -1 is smaller than any valid index. So what you want to do is pick the smallest number that's not -1. Let's look at a few examples. Here, TAA index is -1, and TGA index is 3, and TAG index is 6. What index should you pick for the stop codon? Well, we want 3, because it's the smallest number, which is not -1. Notice we can't just pick the minimum one, because that would give us -1, which is not a valid value here. What if we had 5, -1, and 8? We'd want 5. Likewise, with 10, 4, and -1, we'd want 4. And with -1, -1, and 11, we'd want 11. Let's think about how we can express this decision process algorithmically. In the first example, we compared these 2 numbers first. Even if you think you're comparing all 3 at once, you're really comparing 2 at a time, very quickly, and perhaps without thinking about what you're doing. Of these 2 values, we prefer 3, since the alternative is -1. And then we compare 3 against 6. We choose 3 since it's smaller than 6. In the second example, we'd compare 5 to -1. Then we'd choose 5 and compare this against 8. In this choice, you'd pick the smaller, which is 5. In the third example, you'd compare 10 against 4. You choose 4 because it's smaller. And then you'd compare 4 against -1 and choose 4. In the final example, you're comparing -1 against -1. It doesn't really matter which you pick, they're the same. You then compare -1 against 11, and you choose 11. Note, you should think about what you would do if all 3 values were negative. What would that mean? It would mean that no valid stop codon exists. We'll have to use that in our code. Now, how do we think through how we made these choices? We're only going to look at the logic involved in making the choice between one pair. That same logic will work with the second choice. In the first example, we picked TGA index because TAA index was -1. In the second example, we picked TAA index because TGA index was -1. In the third example, where neither is -1, we picked TGA index because it's smaller than TAA index. And in the final example, it didn't matter which we picked since both were -1. Let's write down what our logic is for making that selection. If TAA index is -1, we'd want to pick TGA index. But that's not all there is to it. We'd also choose TGA index if both TGA index is different than -1 and TGA index is less than TAA index. Notice how we've expressed this logic with or and logical connectives, which let us make complex conditionals out of simple ones. Now let's put that logic into the algorithm we're working on. We'll use that logic to pick between TAA index and TGA index, and we'll store the best choice there is in a variable called min index. Then we'll choose the same logic to choose between min index and TAG index. If min index is -1, there were no valid stop codons, so we'll give back the empty string. Otherwise, we've found a gene. Now let's see how we express these ors and ands in Java. You can express and with 2 ampersands. This is a Shift 7 on most US keyboards. We can see in this example if x is less than y and y is less than z. you can express OR with two vertical bars, also called pipes. On most US keyboards, this symbol is Shift backslash, and we can see an example here. If A is greater than B, or C is less than D. In the particular case of the algorithm we're working on, you could express the step as shown here. Notice how the OR corresponds to the two vertical bars, and the AND corresponds to the two ampersands. AND OR have special rules called short-circuit evaluation, which basically means that if Java can figure out the result of an entire expression involving AND and OR by evaluating only the first operand, then Java will skip evaluating the second operand. Let's look at an example. Suppose x is 8 and y is 1. X is less than y is not true because 8 is not less than 1. So x less than y evaluates to false. There's no reason to evaluate y less than z, because whether it's true or false, the whole AND expression will be false, because false and anything is false. For OR, consider this example, and suppose A is 3 and B is 1. Here, A is greater than B is true, because 3 is greater than 1. So the whole OR expression will be true regardless of whether C is less than D or not. So there's no point in evaluating the expression C less than D, because true or anything is true. Why is short-circuit evaluation important? If you skip evaluating y less than z in this example, it doesn't really matter so much. But it's much more useful when the second operand could crash your program if it's evaluated. For example, here we're checking if x is less than the length of a string and that the character at the xth index of the string is the letter A. If the first condition is false, then x is not a valid index. It's beyond the end of the string. So trying to get the xth character with the .char method would crash the program with a string index out of bounds exception. But fortunately, this line of code is safe because of short-circuit evaluation. The .char method will never be called when x is greater than or equal to the length of the string. Relying on short-circuit evaluation is a great example of defensive programming and one of the tools in your Java programming toolkit. Have fun! Hi, welcome back to Gene Finding yet another time. In this version of the program that we're writing to find genes, we're going to make one small change to what we return when we look for a stop codon, and that change is going to mean that we have to use some complex Boolean expressions using ANDs and ORs to make our code work properly. So as we've already seen, the one small change we're going to make is that instead of returning DNAStir.length to indicate that no stop codon was found, we're going to return -1. That's a good value to return to indicate that nothing was found, because now our code mirrors what, for example, the indexOf method in the string class uses. It uses -1 to indicate that no string was found when searching. Now our findStopCodon method also returns -1. Now that change means that our test function won't work correctly. Remember, we had a test function down here. These functions will now fail because they didn't find that. So to see that very quickly, I'm going to run this new class, create an object on the object workbench, and test the find stop codons. And you can see I got an error 26 twice. And that's because in my program, I had, if it's not equal to 26, so if I change that to -1, compile, and now test my program again, finding stop codons, I can see that my test's finished. So my test program needed to change to recognize this return value of -1 rather than the length of the string. Now I'm confident that my stop codon method with this one small change works correctly and that it returns -1 to indicate that no stop codon was found. That means my find gene method is also going to need to change. Rather than using math.min, I'm going to need these Boolean expressions that you've just learned about. And I've put here in my comments what those Boolean expressions are supposed to do. So I'm going to simply translate this stuff, the comments from my 7-step process, into code. And what that code says here is if TAA index is equal to -1, or, and we use that double vertical bar for or TGA index is not equal to -1 and TGA index is less than TAA index. Now that's a lot. So let's look and make sure we got that right. It says if TAA index is -1 equals -1 or TGA index is not equal to -1 and TGA index is less than TAA index. In that case, it says set min index to TGA index. So I'm going to say min index gets TGA index, just as it says there. That means I'm going to not use these versions of min index, which were from before. But if I compile this code, I'm going to get an error message, something about temp. So if I comment that out, let me comment all of these out. Now I get that variable min index isn't known. So I'm going to define min index, and I need to give it a value. I need to give it some value. I'll just give it 0. I'm going to put in my else statement here what it says to else set min index to TAA index. Else min index gets TAA index. So what I've got now in my code is a translation of if TAA index is equal to -1 or TGA index is not equal to -1 and this expression, then set min index to TGA index, else set min index to this value. Then I still have yet another Boolean expression to write. I need to write if min index is equal to -1 or TGA index is not equal to -1 and TAG index is less than min index. In that case, my comments say set min index to TAG index. So I'm writing that. I'm simply translating this into my code here. Finally, it says if min index is equal to -1 rather than DNA.length, return the empty string. Otherwise, return this. My program compiles, well, almost compiles. I forgot a second parenthesis up here, but that's an easy thing to fix. Well, maybe not fixing it that way by erasing it all. Maybe I should type in a parenthesis instead. Now when I compile my program, it works. How do I test this? Before, in the previous version, I didn't have a test program, a test method. Now I do. I have my test method, find gene. So I'm going to try that out, see if it works. Right-click to create an object. Right-click to testing find gene, and it just simply printed tests finished, which is what I wanted, since in find gene, I looked for a gene. I found this start codon, and I found this stop codon, TAA. Now, I could change this TAA to a different stop codon, and I would keep testing those to make sure that my method works correctly. I'll leave that to you, because as we've already seen, testing is as important as writing your code, because you need to be sure your methods work correctly. Have fun testing, have real fun programming. Hi. So far, you've written a method to find a gene, and gradually improved it. It's gotten much more sophisticated than when you first started, although it's still a bit of a simplification of what you'd actually do. Rather than continuing to refine this method, let's ponder a different facet of searching for genes. So far, you've only been looking for the first gene in a string. However, strings may have many genes. What if you wanted to find them all and print them all out? You can already find one, although you might want to make some slight adjustments to the methods so you can start looking midway through the string. Since you can find one, and you want to find many, you want to repeat steps using a loop. Loops should be getting pretty familiar by now. Since you might want to repeat things as long as there are more genes, you could make use of the while loop that you recently learned about. However, there's a bit of a difficulty here. We won't know if there are more genes until we start searching for them. This may make it seem hard to write the loop condition. There are many ways to deal with this situation in code, but the one we're going to teach you about is how to use a break statement to leave the middle of the body of a loop. We'll work through a slightly shorter example than we normally walk through in developing the algorithm to print all genes. If you don't understand this completely when we finish, pause the video and work through steps 1, 2, and 3 yourself. We're going to show you how it operates on this DNA string as we write it. First, we're going to set start index to 0. Start index will represent where we start looking for the next gene. Then we're going to repeat some steps, as long as there are more genes after start index. We want to find the next gene after start index. We want to print that gene out, and then set start index to just past the end of the gene we found. To show you how the algorithm would continue working on the string, we then go back to step 2 and keep repeating these steps as there are more genes after start index. Notice, this is the difficulty we alluded to before. We need to know if we will find more genes or not, but we haven't looked for them yet. We'd find the next gene, print it out, update start index, and then realize we should stop repeating steps because there are no more genes. However, we have this difficulty. We need to know if there are more genes in step 2, but we don't look for a gene until step 3, which makes the algorithm a bit awkward to implement. Really, we'd like to make a decision about whether to keep going or to stop right here between steps 3 and 4. Here's a slightly modified version of the algorithm which does exactly that. Notice that our repetition instructions no longer have any condition. They just say, repeat these steps. We'll figure out later when to stop. Likewise, we now have another step in the middle of the loop that says, leave the loop if we did not find any genes. This will be much easier to implement once we learn how to translate these kinds of steps into code. For step 2, repeating steps without checking any particular condition, you can simply write while true. If the condition of a while loop is simply true, the code will always enter the loop body when we reach the top, because true always evaluates to true. The other new piece of Java syntax we'll need is the break statement. This is how you say, leave this loop. In this example, we've translated if no gene was found into an if statement that says if gene.isEmpty. The isEmpty method for a string returns true if the string is the empty string, and false otherwise. Remember, our gene finding method returns the empty string whenever it can't find a gene. Inside the if statement, we've seen leave this loop translated into a break statement. A break statement, which is written in Java simply with the keyword break followed by a semicolon, causes Java to leave the current loop, regardless of whether it's a while loop or a for loop or any kind of loop you might yet learn about, like a do-while loop. Basically, Java jumps past the close right curly brace that ends the loop. Now we know how to implement these steps. Let's turn the algorithm into code and try it out. We'll find every kind of gene there is. Have fun.
All right, so you've been learning about while loops and break statements and working on your gene finding algorithm. And your current task is to write a method which will print out all the genes in a sequence of DNA. So we have here the print all genes method, which takes in a string for the DNA and has the algorithm or pseudocode that we came up with in a previous video. Now, we have earlier here in this code the gene finding algorithm that you developed along with Owen in a previous video. And we're just going to make one small change to it. I'm going to have it take one more parameter to say where to start. And this is going to let us start looking for a gene somewhere in the middle of the sequence of DNA. So once we've found one at the beginning, we can start looking for one after that by passing in this index. And we'll just pass that to index. I'll have to tell it where to start looking for the first start codon. So with that small change, we're going to go back here and start translating our algorithm into code. The first thing we said to do was to set the start index to 0. So we haven't made a variable called start index yet, so the first thing we need to do is declare start index. It's going to be an int since we're setting it to 0. It's going to tell us a position in a string, also a good clue that it's an integer. And then we're going to repeat the following steps. So you're used to repeating steps by now. You've done things for each pixel or each of a variety of other things before with for each is a lot. You've also seen some examples of while where you've had a condition for as long as something. But here we want to repeat some steps and then figure out somewhere else inside those steps when we're done. So we're going to write while true and then put curly braces around our steps. And then we're going to go in here and we're going to start doing stuff and then figure out when we want to stop repeating these. Now we want to find the next gene after start index. Finding a gene is a big complicated step. You've been devoting lots of effort and thought into how to do that. Fortunately, we've abstracted that out into a method so we can just call it and let find gene that we've already written do all of that work for us. So what does find gene take? It takes a string for the DNA and an int saying where to start, and then it returns a string. So here we want to call find gene, passing in what DNA? Well, this DNA that we're working with. And where do we want to start? At start index. And then it's going to give us back a string as its answer, so we want to give that a name. I'm going to call it current gene. We didn't say to give it a name in our steps, so we kept referring to it without a name. Well, we kind of know what we mean, but it's good to give things names in your steps anyways. And now we can refer to that gene that we found. If no gene was found, leave this loop. So if something is the case, do some other steps. By now, you should be getting very familiar with if statements. So if no gene was found, how do we know if no gene was found? What does find gene do if there's nothing left? If you don't remember, we can go back up here and look. We can see that it returns this empty string. So we want to know, is current gene the empty string? Fortunately for us, strings have a .isEmpty method, which will tell us if they're the empty string. How would you do that if you didn't know? Well, you could go look at the Java documentation. Are there other ways to figure out if a string is empty? Sure. You could see if its length was 0, for example. Any way that you can find that works is a good way to do it. All right. So if this gene is empty, if current gene is empty and we didn't find it, what do we want to do? We want to leave this loop. That is, we want, Java's executing along and it gets here, we want it to jump down here past this loop. That's exactly what a break statement does, which you just learned about. So we would get here and then come down here. We've basically put the loop condition in the middle. All right, if we don't break out of that loop, we want to print out that gene. System.out.println, hopefully you're getting somewhat familiar with that. We can print out that current gene. And then we want to update start index to be just past the end of the gene. All right, so now this seems a little tricky. Like we wrote a step that's a little bit complicated and maybe we have to think it through a little bit. So let's just go down here to where I've got some testing and think about what we're going to do. So I've written some methods to help us test. And let's think through one of these cases here. So so this test on just prints out that we're testing it, and then does print all genes. So we say, okay, start index is going to be 0. We're going to find this gene right here, which is length 9, right? And so then after that, we would want our new start index to be 9, okay? So we might think, aha, we just want to add the length of the gene, right? That got us from 0 to 9. That's a good first guess. Now let's think about this next one. So then we're going to go and we're going to find this next gene here, which is length 3, 6, 9, 12, 15. But that didn't start right where we left off, right? So if we were to only add 15, we'd end up here in the middle of this gene. And we want to end up over here. So what do we need to do? Well, we need to add the length to the start position of this gene. How can we find that gene? Well, index of is becoming your friend, right? So start index is going to be DNA.index of current gene starting from start index plus current gene dot length. Right, that seems kind of magical. Let me just explain that again really quickly. Right? We want to find where that current gene was in the string. We can do that by looking for it again, starting at start index. So that's going to tell me, this gene was right here. And then we can add its length to end up past here. That'll work for this first one because looking for this first gene from start index of 0 is just going to give me 0. And then when I add its length, I'm going to end up here. All right? If that still doesn't make sense to you, work it out on your own. So now I'm going to hit compile. All is well there. And I'm going to come over here and I'm going to make a new object. And then I'm going to run my test method. And you can see it says, all right, I'm testing print all genes on this sequence of DNA, and it's got 2 of these. Back over in my code, I tried to make this a little easier for us to see. So we've got this, this gene here, and then we've got this gene here. And these little V's were just for me to keep track of the codons. And those were what it printed here. I tested it on the empty string. I wouldn't expect to find any genes in there, but it's always good to test on these like wacky corner cases where maybe our code would break if we weren't careful. We didn't find any genes, but our code didn't crash either. That's really good. And then on this one, where we have this one long gene here, which we found and printed out, and then this really short gene here, which we also found and printed out. So that worked well. And the important thing here, the new lesson, was this while true, figure out if we want to keep going in the middle, and then break.
All right, now you can iterate over all the genes in a DNA string and print them out. If you wanted to iterate over the genes in a DNA string and do something else to them, the algorithm would be pretty similar. In fact, for whatever you want to do with each gene, it would look pretty much like this. The line in blue is the only thing you would change to do whatever you might want to. Maybe printing only those genes that meet some condition, counting genes, saving them to a file, building a web page with all of them, or anything else you can think of. So, if you wanted to do these other things, you might copy the algorithm you have pasted, paste it into a new method, and edit that line to make small changes. This approach works, but it's generally a bad idea. Why? Well, for one thing, copy and paste is error-prone. You might forget to change some things that you need to. Even worse, if you find a bug in your original implementation after you have made copies, you need to go fix every copy you made. It is also tedious. You have to go find the method, copy and paste it, and change it. This may not be so bad if you want one variation, but if you want to do 5 different things, it's pretty boring. And finally, it indicates bad programming design choices. Whenever you find yourself wanting to copy and paste, there's almost always a better approach. Let's take a moment to see something that we could improve about this algorithm. Why it would make a lot of work if we leave it as is and copy, paste, change, and then we'll understand the motivation for how to fix it. This is our algorithm to print all the genes in a string. We're going to condense it down to a small description at the bottom, and then copy and paste it and change line 5 to print only the genes with a high CG ratio. And then we'll condense that down to a short description. Now we're going to copy, paste, and edit to make several other algorithms to do various things with the genes from our DNA string, like printing genes in HTML, writing genes to an output file, counting genes with the codon CGA, or whatever else you want to do. All of these algorithms are the same except for the details of what they do to the DNA string. So at first, copying and pasting does not seem like a big deal. Later, we end up with some other DNA data which list all of the genes in a file, one gene per line. We need to do the same sorts of operations on this data too, but the algorithm will be slightly different. It will have a for each line in the file loop. Then do the same operations for the genes. With our copy and paste approach, we now need to write and test 6 algorithms. They are pretty similar to each other, so it may not be so hard, but it's tedious, error-prone work. Then if we end up with some other source of data, we're going to have to go make all 6 algorithms again for that data source. Likewise, if we end up with a new operation that we need to do, we're going to have to write 3 copies of it, one for each data source. Ick! What a mess! What we would really like to do is redesign our algorithm to use separation of concerns. Our initial algorithm does 2 tasks. One is getting all the genes from some source of data, and the other is printing them, or whatever else we want to do to each of them. We would like to split these up by having the algorithms that find the genes put them into some structure that can hold a list of all the genes. Then having the algorithms that print the genes, count the genes, or whatever else we want to do to the genes, they should operate on that list. Now, if you need to add some new source of data, you just write a way to get its genes into our list, and it automatically works with every processing algorithm you already wrote. Likewise, if you need to write a new processing algorithm, it automatically works with every source of data that you already wrote. No copying and pasting is ever needed. So what is this thing that can hold all the genes your algorithms find? We're going to start by using a class from the edu.duke package called storage resource, which is a simplified way of doing this. Later on, once you have learned a few more concepts, you will transition to using the standard java.util.ArrayList class, which has similar functionality, but it's a lot more complex. Thank you.
Okay. Now you've learned that you want to store your data in a list so you can separate concerns. You learned you'll start out with our edu.duke.storage resource class, which is a simplified way of doing this. What exactly is a storage resource and how do you use it? It's a class that holds a collection of strings. You can call .add to put a string into the storage resource. You can also use .data to get an iterable, so you can iterate over all the strings that have been put into the storage resource you created. There are a few more methods, and you can read about them in the DukeLearnToProgram.com website, where there's a document page for the storage resource class. Let's look at an example of using it. First, we're going to declare a variable SR of type storage resource. Once we've declared the variable SR of type storage resource and initialized it to a new storage resource, we'll see that it's empty. Then we might add a string, such as hello. Then we might add another string, such as world. And then we could iterate over all the strings in the storage resource by writing a for each loop and using sr.data. Let's see what happens when we step through this code. The first line declares a variable, so we'll make a box for it labeled SR, and then calling new creates a new storage resource. It's going to be an empty list of strings, which the SR variable will refer to. will add the string hello to the storage resource's list of strings. Similarly, sr.addWorld will add world to the list. Now we're at the for each loop. We're iterating over sr.data. So we'll make a variable we're going to use to iterate and have it refer to the first item in the storage resource object we created. By referring to the first item in the storage resource object, we'll be able to print it. Here it refers to the first item in the storage resource, the string hello. Inside the body of the loop, we print out s, so we print that. Then we go back to the beginning of the loop and refer to the next string in the list, in this case world. So we print world as we enter the loop. Once we've reached the end of the loop, we go back to the beginning of the loop and see that there are no more strings in the list. So we'll go past the loop and we're done iterating over the elements of SR. If you want to learn more about other methods in storage resource, or you forgot about the details of the ones we discussed here, you can find the documentation for this class on DukeLearnToProgram.com. Finally, let's see what our algorithm would look like to find all the genes and put them into a storage resource. It's pretty much what you had before, as we show here, except we've made 3 changes. First, at the beginning of the algorithm, we make an empty storage resource to put the strings we find, the genes, in. After making the empty resource, we do something to each gene we found. We add it to the storage resource. Finally, at the end, we give an answer. We use the storage resource with all the genes in it. Rather than printing them out, this method will return a value to whatever code called it. So the caller can use the storage resource and the data inside it for whatever purpose they want. That could be to print it, or it could be to process that data further. Have fun with storage resource.
Hello, and welcome to this introduction to using Java to help find trends, patterns, and make a conclusion about information found in data. You see here 2 screenshots of spreadsheet programs that have been used to analyze data over many, many years. On the left is a screenshot of a Google Docs spreadsheet that you can use today. This program analyzes data and runs in the cloud. It is accessible via a browser or a mobile app on all kinds of devices all over the world. On the right is a screenshot of VisiCalc, the first spreadsheet program that launched in 1979 and ran only on Apple II computers. In general, spreadsheet programs work on data formatted in rows and columns, tabular data. You'll be able to write Java code to analyze such data as well. Spreadsheets revolutionized so many industries and launched new ones by taking seconds to model what-if scenarios that had previously taken days to perform. The link here is to a podcast describing the development of VisiCalc and the industries that were transformed by these programs. Today, data that can be analyzed by software programs is often made publicly available through government and nonprofit websites. Typically, data is produced in CSV files, files in which the different data values in each row are separated by commas, thus the name comma-separated values. You're going to learn how to write Java programs to analyze data stored in CSV format. Using spreadsheet software is a great way of finding patterns, information, trends, and visualizing data. But sometimes a spreadsheet program isn't enough to solve every problem easily. There are many different spreadsheet programs, so a common format is useful. The CSV format makes it possible for data to be portable between different types of software used to analyze data. Furthermore, you can write your own Java programs to analyze data using the CSV format. Common formats often have standards. For example, the Internet Protocol, or IP standard, determines the format for the packets that transport information across the Internet. The IETF, or Internet Engineering Task Force, that made the IP standard also created a standard for CSV files. Other groups have made different but related standards for formats used in different software programs. In this lesson, you will learn how to use an open source software library, the Apache CSV parser, as you learn more about Java programming. This software library will allow you to solve problems that would be really difficult to solve using just a spreadsheet. Let's get started with this.
Hi. The code you're about to see will show you how to access a comma-separated values file named foods.csv using Java. To better understand that program, here are 3 views of the data in the foods.csv file. The file itself looks like this, with the first row having labels used for each column. This is the header row. You can see the labels for each column of data. And you can see the data in each row is separated by commas. Here's the view using the spreadsheet program Microsoft Excel. Some of you may have used this program before. The Google Sheets program that runs in a web browser is free software that also allows you to manipulate spreadsheets. Here's the view of foods.csv from that program. You can see the first column has the label name, the second column has the label favorite food, and the third column has the label favorite color. Let's get coding. I'm going to walk through a simple example of using the CSV libraries that we have in our course so that you can understand how to create a CSV parser and how to use it in the most basic ways. More complex ways will be something that you learn in later parts of this course and that you can read about when you study the API. So I have a simple first CSV example. I'm going to open up the code so that we can see a few things, but rather than studying it in detail right now, I'm going to run it very quickly so that we can understand how it works, and then we're going to walk through each piece and make one small modification. So my class is already compiled. I can see that because there's nothing shaded here. I'm going to right-click and create a new object on the object workbench. I already have one, now I have 2. I'm going to read the food from that. That pops up a file dialog. This is an example of our directory resource, and I choose foods.csv, a CSV file, and the program comes in and reads and prints Drew, Owen, Susan, and Robert. So I'd like to try to understand why it's printing those names, and then see if we can find some more information in the CSV file other than just our names. Looking at the source code again, I'm going to notice a few things. First, I've imported the edu.duke libraries, which is common in many of the examples we do. Because I'm using the CSV parser, I need one more import, and that's a very complicated one, but kind of something that you'll just be able to cut and paste over a while. org.apache.commons.csv. We're using an open source library for our CSV parser, and we've made it a little more convenient to use in a way that I'll explain. I have one method, read food. I've created a file resource object that's using our standard library. Because it has no parameters, the file resource object will pop up a dialog and allow me to navigate to the file I want to use. I just showed you using foods.csv. Then I ask the file resource object, fr, to give me the parser, get CSV parser. This is the new class, the CSV parser class, that's part of my Apache library that you can see highlighted on the screen. I now loop over the iterable, that is the parser, getting a CSV record each time. So I have 2 new classes here, the CSV parser class and the CSV record class. The CSV record class has one method that I'm using, get, and that allows me to get one of the records on the line of that CSV file. As you may remember, CSV files consist of several elements of data separated by commas. One of the elements is named name in this case. Since I've studied the CSV file, I know that one of the other elements is named favorite food. So if I ask the record to get me the field, the element that's favorite food, that will do it. I'm going to print this one with just a space after it. So notice I've changed the print lin to just print. That stays on the same line. Print lin will finish the line. I'll show you how that output works. My class is compiled, no errors. I'm going to create a new object on the workbench by right-clicking, which is what I normally do here. So I'll select, right-click, create a new one. And then on the object workbench, I'm going to read, navigate to the foods.csv file, and notice, now I have Drew's favorite fruit is chocolate, Owen, its favorite fruit is pineapple, Susan really likes cake, and Robert likes pizza. One more example. it turns out that in addition to favorite foods, in this CSV file, there's also a favorite color. So I'm going to print the favorite color. We'll look at those briefly, and then we'll review finally. So favorite color, and I should put a space at the end of that line so it's easier to read. I'll compile that. When I create the new object, it appears on my object workbench. I'll run that, navigate to the foods.csv file, and lo and behold, Drew's favorite color is green. Surprisingly, Robert's favorite color is green too. If you're a very astute observer of the courses that we've done so far, that might make sense to you. Susan loves purple, and I like blue. That is running through. Let me review one more time. In this CSV file that this program read, there are 3 fields: name, favorite color, and favorite food. If you tried to get another field, so for example, I decided to say that my favorite number was get favorite number, so I'll say get favorite number. That will compile, and when I try to run this example by making a new object and running by right-clicking, sometimes I can't right-click too well, open foods.csv, and I've got all kinds of illegal arguments except for favorite number not found. My CSV file does not have a favorite number field, and so I could not open that. When we study this in more detail, and when you read the API, you'll see that there are ways that you can avoid trying to access CSV elements that don't exist. But for right now, we've seen use a library appropriately, that's org.apache.commons.csv, get the CSV parser from a file resource object, and then loop over the parser, which is an iterable, to get records one at a time. Have fun with CSV and finding information from data.
Welcome back. Now that you know a little bit about the basics of working with CSV files, it is time for you to solve a problem using them. Here we have a CSV file which shows export data for 218 countries. The columns are the country name, the main exports, and the total value of their exports in 2014 in US dollars. A problem you might want to solve with this data is to find which countries export a particular item. For example, you might want to print all of the countries which export lobsters, or all of the countries which export iron. There's a lot of data in this file. Way too much to look at by hand, which would be tedious and error-prone. Instead, you would rather write a program to perform this analysis for you. As always, we will walk through how you write such a program using the 7 steps. Step 1 is to work a small instance of the problem by hand. Here, we've cut the table down to 4 countries and only listed a few exports for each of them. Which of these countries exports coffee? After looking at the table for a few seconds, you can see that Madagascar and Malawi export coffee, and Macedonia and Malaysia do not. Next, you need to write down what you just did. If you just say, I just looked at it and saw the answer, that will not help for step 3. Instead, you need to think through what you did in a more step-by-step fashion. How did you look at the table and see the answer? You probably looked at the first row's export column and saw that it did not contain coffee. Next, you looked at the second row's export column and saw that it contains coffee. So you wrote down Madagascar. Next, you looked at the third row's export column and saw that it also contains coffee. So you wrote down Malawi. Finally, you looked at the fourth row's exports column and saw that it did not contain coffee. Thinking through this in a step-by-step fashion leads to these 10 steps for this particular instance of the problem. Now we are ready to look for patterns and generalize. Notice how you are doing very similar things for each row. This similarity suggests you will eventually want to loop over each row. However, there are some differences in the steps for each row that you need to think through before you can express this algorithm in terms of for each row. The first difference you might notice is that on line 5 you wrote down Madagascar, and on line 8 you wrote down Malawi. Where did these particular words come from? They are the value of the country column for the row you are looking at. The next difference you might notice is that you do not write down the country for the first and fourth rows, but you do write it down for the second and third. How did you know whether to write the country down or not? You made this choice based on whether or not the row contained coffee in the exports column. Now that you have figured out how to operate on each row in the same way, you can write down the generalized steps in terms of for each row in the CSV file, generalizing over how many rows the file has. Now that you have a general algorithm to solve this problem, it is time to test it out. Here is a table of data which contains 2 countries. Use the algorithm to find out which ones export lobster. Is this algorithm correct? According to our algorithm, Brazil is the country which exports lobster. Oops, that's not correct. We should have gotten Anguilla. Did you test the algorithm carefully enough to notice this mistake? The problem is that our algorithm always checks for coffee, not for whatever export we are interested in. We should have thought this through as we generalized, but we missed doing that. This is exactly the sort of problem step 4, testing your algorithm, is intended to catch before you write code. You can fix this algorithm by referring to the parameter, we'll call it export of interest, which indicates which export you want to look for. Making this correction to the algorithm will have it yield the right answer on this test case. Now that you have an algorithm, it's time to write the code. Okay, now that we've developed our algorithm to figure out which countries export a particular item, it's time to turn that algorithm into code. I'm here in BlueJ, where we've created a class and imported edu.duke.star, which you've used for many things, and org.apache.commons.csv.star, which you've learned recently is what you need for the CSV parser class. I've written a method here, list exporters, which takes in a CSV parser, so that's going to be the CSV parser that's already open for the file you want, and a string for the export of interest, and I've written down comments here for the algorithm we just devised. So the first step in our algorithm, which has a slight typo in it, said for each row in the CSV file, you've already learned that that's for CSV record is the type of item that you iterate over in the CSV file, and we'll call it record from the parser. And I'm going to put curly braces around all of the steps that go inside of there. And then we said, look at the exports column. You learned before, I'm just going to call that exports. This is record.get and the name of the column you want, in this case, exports. Check if it contains export of interest. So now we need to check and see if this string export contains export of interest. One way we could do that, which you've seen before, is export.index of export of interest is not equal to -1. Now if you were to look in the Java String API, you could see that there's a little bit more readable and convenient way to do this with a method that just is called contains. These two will do the same thing, it's just a little more clear to someone reading the code what you're trying to do if you write contains instead of index of equals -1. I'm just going to put that back where it goes. And then we said, if so, write down the country from that row. So I need to first get the country, string country equals, and again, I'm going to use record.get country to get the country column from that row. And then if I want to write something down, I would print it out. Okay, and then my curly braces all match up. I'm just going to hit compile. It says it compiled with no syntax errors. Now, as with other things, making a CSV parser in the BlueJ object workbench is a little complicated. So we're just going to make a method here to help us test this, which is going to be who exports coffee. It's going to take no parameters, and it's going to tell us which countries export coffee from a particular data set. So I'm going to make a file resource which you've seen many times before. And as you may recall, if I create a file resource without passing in any parameters, it will pop up a dialog to let me pick what I want to choose it from. And then I'm going to want to get the CSV parser out of that. That file resource has a way to give me a CSV parser, which will parse that file data. And then I want to list exporters from that parser for coffee. And I'm going to compile this again. It tells me invalid method declaration, return type required. I forgot to tell it what type it returns. In this case, I don't want to return anything since I'm just printing things out. So I'm just going to write void there. And then I'm going to try to compile again. That compiled just fine. I'm going to come over here, and I'm going to make a new one of my objects. And I'm going to say who exports coffee. And then I have this export data.csv file, which is going to list a whole bunch of countries. Now, we're trying to test out our code. We don't know if this is correct. How would we know this? Well, we'd have to go through that entire CSV file and check, did we get everything that exports coffee? That would be really tedious and is the whole point of writing the program in the first place. So what we should and can do instead is write a much smaller file. Here's the one that we used in the slides. And we can test our code on that instead. So if I come back here and I do who exports on, this is export small.csv. It says Madagascar and Malawi, which we know is the right answer. So that gives us more confidence in our code, and we can be more certain that we got the correct answer on the larger file. So there's the code for that. And now you can do similar things yourself.
Okay, so now you know how to solve the problem of analyzing CSV data to find out which countries export a particular good. In this lesson, you learn the mechanics of using Apache's Commons CSV package, a library for working with CSV data, using the CSV parser and CSV record classes to operate on the data in CSV files. You devise an algorithm to analyze a CSV file and find out all the rows that meet a particular criteria. In this case, which ones export a specific good. But the same basic ideas would work for other criteria more generally. And, of course, you implemented it in Java, putting your newly gained knowledge of the CSV library to use.
Welcome back. Now that you know a bit about working with CSV files, it is time to learn how to analyze numerical data in those files. For example, here we have a CSV data file about the weather at the Raleigh-Durham Airport for January 1st, 2014. We have this data for every day in a couple years with one CSV file per day. Each row contains information about 1 hour of weather, and there are a variety of columns such as the temperature in Fahrenheit, the dew point, the humidity, etc. If you are studying weather patterns, you might want to analyze this data and ask a variety of questions. Of course, the techniques you will learn are applicable to other types of data too, so you may find them useful in a variety of other fields as well. One question you might want to ask is, what is the maximum temperature? That is, when is it hottest? If you were doing this just for the data on one particular day, you could just look. There are only 24 entries. Or use the max function in a spreadsheet. However, what would you do if you wanted to find the maximum temperature over many days, such as for an entire year? You certainly do not want to look through all of the data by hand, and importing 365 files into your spreadsheet would be quite tedious. For something like this, you would want to write a program to do the work for you. In this lesson, that is exactly the problem you will solve, finding the hottest day of the year. For the purposes of this example, we are going to say that the hottest day of the year is the one with the highest maximum temperature. A related but slightly different problem is to find the day with the highest average temperature. We're not going to walk through that problem, but you could certainly do it after this lesson. The plan to write this program is to start by learning about dealing with numerical data. The CSV parser will read the data as strings, which have to be converted to numbers. Once you know how to convert strings to numbers, we'll start with a smaller piece of the problem, just finding the maximum temperature on one day. We'll walk through the algorithm and the code development with you. You will want to test your code to be confident that it is correct before proceeding. Once you are confident in your code to find the maximum temperature on one day, you will want to build on it and find the maximum temperature for many days. This will let you find the maximum temperature in a year. So let's get started.
Welcome back. As you work with data in CSV files, you may encounter numerical data, such as this. Here we have a variety of numbers, such as years. However, the libraries you use to read a CSV file will read this data in as a string, the sequence of characters 1493, not the integer 1493. If you want to manipulate this data numerically, adding values, finding the largest, or some other task, you will want to work with the data as an int or a double. So what would happen if you tried to write a line of code like this? Int value equals row.getYear. When you try to compile it, you would get an error message here that the types are incompatible. You are trying to assign a string to an int. Let us look a bit more at this error. If you look at the documentation for the CSV reader, which we show here, you will see information about the get method. In particular, you can see that its return type is string. Because that method returns a string, this entire expression, row.getYear, has type string. Java knows that it will be a sequence of characters. However, that is not the same type as int, which is the type we declared value to be. This raises two questions we will answer for you. First, why is this a problem? Sometimes Java can automatically convert between two types, so why can't it convert a string to an int? It seems like if we have the string 1493, Java could just figure out that that should be the number 1493. However, it cannot do this in this case. The second question is, of course, how do you fix it? To see why Java cannot automatically convert a string to an int, consider what would happen if the string did not have numerical digits in it. For example, suppose our CSV reader read the string hello instead. What would you expect Java to do for this line of code? The rules of Java require the compiler to reject this line of code because there is no guarantee that you can meaningfully turn any string into a number. Another consideration is that the string 1493 has a very different representation from the number 1493. Even though everything is a number, the type of a piece of data describes how that number is represented and interpreted. We will not delve into the details of the representational differences here, but it takes some work to convert between the two. Accordingly, we would have to execute some code to perform the conversion algorithm. Such an algorithm would examine the digits in the string and compute the integer that they represent. We are not going to write this algorithm ourselves because it's already built into Java. You can just call integer.parseInt to convert a string to a number. Even though it's built in, you still have to call it explicitly to tell Java that that is what you want to do. Here you can see an example of how you can use the integer.parseInt method. You pass in the string you want to convert, and it returns the integer value. If you need to work with numbers that have fractional parts, you can use double.parseDouble, which will accept a string like 42.56 and convert it into the corresponding value of type double, the type to use to work with non-integer numbers. For either of these methods, the string could be invalid. It could be something that does not represent a number. For example, if you passed hello to integer.parseInt, the method cannot turn hello into an integer. So what happens? The method throws an exception, which indicates that an error has occurred. If your program throws an exception, then it will crash. There are ways to make your program handle the exceptions, specifying what to do instead of crashing. But we are not going to go into that more advanced topic here. So now you know that you cannot just assign a string to an int, and that if you need to convert a string to an int, you should use integer.parseInt. Likewise, for real numbers, you have learned to use double.parseDouble. Now you are ready to manipulate CSV data with numbers in it. Thank you.
Welcome back. The first piece of solving the problem of finding the highest temperature in a year, which has its data spread across hundreds of files, is to find the maximum temperature in one day, which always has one file. As always, we're going to start by working a small example by hand in a step-by-step fashion. Here we have 6 rows of data to work with. The first thing you might do is look at the first row, and in particular at its temperature, which is 30 degrees Fahrenheit. That is the maximum we have seen so far, which you will want to keep track of. If you were just working this out with a small data set, you might just remember it in your head, but we will draw a red box around it to be explicit. You might then go through the rest of the data in a similar fashion, looking at each row and deciding whether it is the largest you have seen so far or not. After you look through all the rows, you have found your answer, which in this data file is the last row. Okay, now that we have worked an instance of the problem by hand, it is time to write down exactly what we did in a step-by-step fashion. The first thing we did was look at the first row, in particular its temperature F column. Next, we noted that it has the largest temperature so far. The next step was to look at the second row. Its temperature is not greater than the largest temperature we have noted so far. Then we looked at the third row. Its temperature is 30.9, which is larger than the largest we have seen so far. So we updated our largest so far to be the third row. For the fourth row, we did very similar steps. Saw that 32 was larger than the largest so far, and updated our largest so far. The fifth row was not larger than the largest so far. And the sixth row was larger than the largest so far. So we updated our note of what was the largest. That was the last row. So we are ready to give the answer. In this case, the sixth row was our answer. Now that we have all of those steps written down for this particular instance of the problem, we are ready to find patterns and generalize. The first thing you might notice is that you are doing similar but not quite the same things for each row of the CSV file. As you can probably guess by now, you will eventually write code which loops over the rows to solve this problem. However, before you can do that, you need to think about the differences and find ways to make them the same. The first difference you might notice is that for the first row, we just noted that it was the largest so far. But for later rows, we compared the row to what we had previously noted down as our largest so far. The first row is a bit unusual here because we have nothing else to compare it to. We did something implicit that we did not write down. We check if our largest so far was nothing or something first. We'll need to incorporate that into our generalized steps. The other difference you might notice is that sometimes we updated what we recorded as the largest so far, while other times we did not. We marked the first row's update in purple, as we just discussed how it is different from the others, and marked the steps in red where we did not update the largest so far, and in green where we did. What is the pattern? It is when the current row's temperature is higher than the largest so far's temperature. Thinking through these patterns leads us to the following thoughts on how to decide when to update the largest so far. If the largest so far is nothing, meaning we don't have one yet, then the current row is the largest so far. Otherwise, if the row's temperature is greater than the largest so far's temperature, then the current row is the largest so far. After thinking through that, we can express our algorithms in terms of for each row in the CSV file. For each row, which we will call current row, you will want to decide how to update the largest so far variable, as we have just discussed. We have not said anything about what largest so far starts as, so we should be sure to put that in here. We mentally glossed over this while we were writing down our steps, but we implicitly started with it as nothing before we began looking at each row. We should write that down in our algorithm here. The last step, which we did write down, was to give our sixth row as our answer after we finished looking at each row. Is the answer always going to be the sixth row? No. It is always going to be the largest so far, the row that we have been keeping track of as we worked through the data. We should test this out before we try to write our code. Try it out on these 4 rows of data. Does the algorithm give the right answer? Yes, it does. We are now more confident that we wrote our algorithm correctly, so we are ready to turn it into code. In writing the algorithm to find the maximum temperature in a CSV file, we wrote down steps that do not correspond to anything you know yet in Java. The idea of having nothing. How do you turn that into code? This introduces an important new concept in Java, null. In Java and many other programming languages, null means nothing or no object. This concept is very important as it is common for algorithms to need to refer to the value no such thing. One thing you can do with null is initialize a variable to it. For example, CSV record largest so far equals null means initialize largest so far to be no such thing. Another use of null is when an algorithm has an answer of it doesn't exist or there's no such thing. In that case, returning null from a method is an appropriate way to indicate that no such answer exists. You can also check if an expression is equal to null, which is quite useful in many algorithms. In the algorithm we are working on, you want to check if largest so far is nothing. That is, if it equals null. One thing you cannot do with something that is null is call a method on it. Since null means no such object, it does not make sense to try to call a method on no such thing. For example, this code is problematic, even though it compiles just fine. This second line will cause the program to crash when you run it. You would get an error message like this, which tells you what went wrong. The first thing about this error message is that it says exception, which generally means that something went wrong with your program. The last part tells you what kind of problem you had. Java lang null pointer exception in this case means you tried to do something with null that needed an actual object. In this case, trying to call a method on it. While we are discussing null, remember that all expressions have types. You have previously learned that it is important to know the types of expressions as you write and think about code. This raises an important question. What type of thing is null? We wrote CSV record largest so far equals null and told you that was legal. So it might seem like the type of null is CSV record. But does that really make sense? Would Java be designed such that the type of nothing is a CSV record? Shouldn't we be able to have nothing for other types too? Java actually has a special null type. Unlike other types, you cannot write down the name of this type in your program. You cannot declare variables of this null type, nor can you make methods whose return type is this special type. The literal null is a special type, and this type can be converted into any object type. That is, Java will let you assign it to variables of any object type, return it from methods whose type is an object type, or compare it to any other type of object. You may have noticed that we just said any object type, not just any type. Java has two categories of types, primitives and objects. Primitive types cannot be null. You have seen 4 primitive types so far: int, double, char, and boolean. There are also 4 others you have not seen: byte, short, long, and float. These types are all built into Java, and they are just plain data. They do not have any methods associated with them, and they cannot be null. The other category is object type, which can be null. You have seen many object types so far: file resource, string, CSV record, and pixel, just to name a few. In general, anything with a method in it is an object type. Likewise, any class you write is an object type. There are some other differences between primitives and objects, but they're not relevant yet, so you will learn about them later. Now that we've developed the algorithm for finding the hottest hour, we're going to write the code. So I've already set up the class for us with the imports that we're used to having, and the class name, and the method that we're going to write is this hottest hour in file. And we've already started, we're going to start the process with the pseudocode that we've developed by the end of the last video. So at first it says start with the largest so far as nothing. So we now know that nothing in Java is represented as null. So I'm going to go ahead and set largest so far. I'm going to give it an initial value of null. So now it starts out with null as its initial value, and it's a CSV record, which is what we're planning to return. I'm then going to come down and it says for each row in the CSV file, and that again is our familiar pattern of iteration that we've been using throughout this course, and we're going to use the parser that's been passed in as the parameter as the CSV information that we're looping over in the iteration. And I'm going to go down to the bottom here and go ahead and close this loop so that again I sort of have the idea of what I'm going to do for each record as we iterate over it. Next it says if the largest so far is nothing. So this is the first time that we've seen it, and we're going to check to see if largest so far is null. And again, this is just like we saw in the last video. We're checking to see if the value was null. If it is, we're going to assume that the current temperature, the current record, is the hottest one. So we will call that current row, or we'll assign that largest so far gets current row. That's all we have to do for that if statement. We're just replacing it. Otherwise, and that means else in Java, I'm going to compare the two temperature values directly. That means I need to get those temperature values out of the record. I know that those values are going to be numbers, but I have a decision to make. Should they be integers, whole numbers, or should they be doubles, real numbers? That's right, they should be doubles, because one of the temperatures was 30.9 in our example, and that's a real valued number, which is better represented as a double. So I'm going to set current temperature equal to the current row dot get of temperature F. But getting that value is going to give me a string, and what I really need is a number, so I need to convert that string from a string into a double. So I'll use double.parseDouble to make that happen. Then, because I need to do the exact same thing again, I'm just going to go ahead and paste that line, and I'm going to call this largest temp, and I'm going to get it from largest so far. And now I have two double values, and I can compare them directly. I'm going to check if the current temp is greater than the largest temp, and if it is, then I'm going to replace that value, the one in largest. So I'm going to say largest so far gets current row. So I've replaced it in the two cases that we had checks for, and I'm done with my pseudocode for inside the loops, and I'm going to move to the next line, which is outside the loop, and it said that largest so far is the answer, so I'm going to return largest so far. Now I'm going to compile my code just to make sure I haven't made any silly errors. It says no syntax errors, so now I'm ready to test my code. Let's take a quick look at how the data is organized on the file system and what an actual file looks like. So we have a data folder, and inside of that data folder it's organized into years, and then within each year we have a weather file for each day. So there's 365 or 6, depending on if it's leap year, of those files for each of the years. So that's how it looks on the file system. And then here's how an individual file looks. So in this case I've chosen January 1st, 2015 as the one that I'm going to test, the data file that I'm going to test. And you can see we've got the column information up top, and we've got the column data for each of those. And we have two files loaded up in a spreadsheet because CSV files are easily represented as spreadsheets, so this is a nice way to visualize them. The other method that I've already included in the CSV Max class is test hottest in day, so that we can test our code to make sure that it's right. The first line in there creates a file resource already set to January 1st, 2015. The second line calls our hottest hour in file method that we just wrote, passing it the parser that we created for that particular data set, and then that returns us the CSV record that is the largest one. And then we print out that hottest temperature and the time that it appeared at, just to see when that was, and that's going to give us a sense of whether or not our program is correct. So I'm going to compile our code, and I'm going to come over to the BlueJ environment and create a new CSV Max object, and then call my test hottest day. And it says the hottest temperature was 51.1 at 2:51 p.m. And if I go over to my data file and I look at the temperatures, I see that they are in the 20s, in the 30s, 50, 51.1, back down to 50, back to the 40s, and 42.1. So indeed, the hottest temperature was 51.1 occurring at 2:51 p.m. Let's also check the 2nd of January just to try it on a second data file to see how we're doing. So I'm going to come over and change that from January 1st to January 2nd. I'm going to recompile. I'm going to go ahead and create a new CSV Max and call test hottest day. This time it thinks it was 54 at 12:51 p.m. And again, if I come over and I look at my temperature, I'm in the 40s. I'm now in the 50s, 51.1. I have 54s, and then back down to the 40s. You'll notice that there's actually 4 times when it was recorded as being 54 degrees, and we've recorded the first time that occurred, 12:51 p.m., as opposed to the last time that occurred, 3:51 p.m. So now that I've tested it on 2 separate files, and I've seen that it worked for those, I feel reasonably confident that my code is correct, but I encourage you to test it on more files and try it out on your own and see what you get. Now that we can find the hottest temperature on a single day, let's look over a range of days and find the hottest temperature over that range. For this, I've created a new method called hottest in many days that we'll use to do this calculation. And we'll be using a directory resource for this, which will allow us to select any number of files over at once to compare. As we've done for many examples, we'll create a file, and that will be what the directory resource returns when we say selected files, and we'll iterate over that. And now that we have that file, we'll use that to create a new file resource. And now that we have that file resource, we can actually we can call the hottest hour in file method that we created earlier with the CSV parser, just like we did in our test, actually. And so this code right here that we've already got in our test is exactly what we're going to do, but now we're going to do it inside of a loop so that we can do it as many times as needed. But instead of this one being the largest, this one is only going to be the current temperature, and we're going to have to compare that against the largest so far. So just like in the previous example, we're going to have to keep track of what we think is the largest one so far. So to do that, we will create a CSV record, largest so far. I'll even use the same name. And initially it will be nothing, so I'll set that to null. And then once I get I'm looking through the loop here, I'm going to check to see if the largest so far is empty, meaning we haven't assigned it yet, then I will go ahead and reassign it to the current one that we just got. Otherwise, I'm going to have to compare the two of them again. And again, since this code is going to be very, very similar, I'm actually going to go ahead and literally copy and paste it from my previous implementation. And I'm going to get the current temp. Oh, I'd call that one current row. I like current row. I'm going to call this one current row as well, again, so that we have a similarity of names. And so I'm going to get the current temperature and save that as a double current temp. I'm going to get the largest temperature out of largest so far. I'm going to compare them. If it's greater, I'm going to go ahead and replace it. And then I'm going to close my loop. And so now I've iterated over many days. The main difference is I've called hottest hour in file instead of calling it for a particular row in that day. And once again, largest so far is going to be my answer. So I'm going to return that at the end. I'm going to compile my code just to make sure that I didn't make any silly mistakes. And it compiles, so now let's go on to testing. For testing, once again, I've created a test method, test hottest in many days. In this case, I call the hottest in many days method. It takes no arguments, so there's nothing to pass, but it returns a CSV record, largest, for me to use. I've printed out that the hottest temperature was, and I've also printed out what day it was. I've changed the field that I get to date UTC from time EST, since it could be any day, and now I want some extra information. I want to know what day it actually occurred on. So I'm going to go ahead and compile this and come over to the BlueJ environment. I'm going to create a new CSV max object. I'm going to call the test hottest in many days, and I'm going to go ahead and choose the first 2 days from 2015 just to test, because I've tried those 2 times before, so I know that the hottest day for January 1st was 51.1 and the hottest for January 2nd was 54, so I would expect that the answer is 54 on January 2nd, and sure enough, that's what my answer is. Now that I have some confidence that it's working, I'm going to try it on a bigger data set, and so now I'm going to test for many days, and I'm going to see what it was like for the whole of the year 2014, which is the last year for which we have complete data. And now I'm going to go ahead and say open, and apparently that was 98.1 occurring on July 8th at 10:51 p.m. So now I feel somewhat confident that my code is working. I tried it on a small example, just 2 days, and then I scaled it up to try it on an entire year, something that would be very difficult for me to test by myself, but that smaller data set gave me some confidence that my larger data set was working correctly. Technically, my code is done, but I feel a little uncomfortable about the amount of duplicated code that occurred in both of the methods that I wrote. And I know that it was duplicated because I copied and pasted between the 2 methods. And in programming, that's not a good way to create your programs, because if you have a problem in that piece of code, it now appears multiple times and you have to try to fix it in all those different places. So what I'd like to do is I'd like to factor out that common code and put it in its own method, which here I've named getLargestOf2, so that I can reuse that code in all of my other methods. So the part that I copied and pasted was this if-else statement that appears both in the hottest of many days and in the hottest hour in a file. So I'm going to go ahead and cut that code from that method and put it into getLargestOf2, including at the end returning the largest so far, so that I have the right result. And I don't have to make any changes to the code because in my particular case, I had everything named the same. So both of them call the current one current row and the largest one largest so far. And largest so far should remain the same unless it's null or unless current temp is greater. So in those two cases, I should update largest so far, but otherwise largest so far is the correct value. So that's what my method is going to look like. It's just going to be those two, the if and the else statement and a return of its own. And now I can use that here to say largest so far get largest of 2, and I'll pass it the current row and largest so far. That will do the work of my if else statement, store the result there. And likewise, I can now copy and paste this one line of code into hottest of many files and replace, again, that same if else with that one line. Sorry, I lost my place there for a moment. So I get the current row from the file, and I get the largest of the 2. And now let's go ahead and compile and make sure that I didn't misspell something by not capitalizing it. And then since I copied and pasted that, I have to fix it twice, which is exactly what I was warning you about earlier. And so now, hopefully, since I fixed both of those, it will compile. And now we have to go back and test it just to make sure that everything is correct. So I'm going to create a new CSV max, because even though I moved code around and it shouldn't have changed the functionality, I want to actually make sure that that's true. So I'm going to test the hottest of the day, and sure enough, it gives 54 for January 2nd of 2015. And I'm going to call get hottest in many days, and I'm going to go back and select those 2 days that we've been using for our tests, and sure enough, it still thinks it was 54 degrees. So with those tests, I feel good that the changes that I made in terms of moving code around didn't affect the functionality, but now I feel more confidence in my code because this large piece of code that was duplicated, now I've taken care of and it only appears in one place. So if I ever find a problem with that, I can go back and fix it just in that one place. Okay, so now you know how to solve the problem of finding the row with the maximum temperature in many CSV files. In this lesson, you learned how to convert strings to numbers with either integer.parseInt or double.parseDouble. You saw another example of breaking a larger problem into smaller problems as you first solved finding the maximum in one file, then built on that solution to find the maximum in many files. You learned how to devise and implement an algorithm to find the maximum element in a set of data. And you also learned about the concept of null, which is how you represent nothing or no such object in Java. Hello, you're going to learn the background and coding needed for the mini project for this course. You're going to write programs to answer questions that are very hard to answer using a spreadsheet, but that you'll be able to approach in a straightforward way using the practices, skills, and libraries you've learned about in this course. You're going to answer the question, what's your name this year, given your name in the year you were born? In other words, what name this year has the same popularity rank as your name did the year you were born? You can answer this question for anyone's name, so you can use a friend's name, a singer you like, or anyone. These pictures we will be using to describe what you're going to be doing are taken from a website that offers something similar to what you'll be doing in this mini project. Suppose you are a female named Jennifer, born in 1994. Jennifer was the 21st most popular girl's name in 1994. So one task you'll need to do is write code to figure out a name's ranking for a given year. If you were Jennifer in 1994, what would your name be today? You'll discover via coding that Grace is the 21st most popular name today, where today is 2014, the most recent year for which we have data on names given to babies in the United States. So today your name would be Grace if you were born in 1994 and named Jennifer. But you can also see what your name would be in any given year. Here we see a summary showing your name in several different decades. Jennifer in 1994 would be Barbara in the 1970s. That means Barbara was the 21st most popular name in the decade of the 1970s when taken together. Because we have data for the United States going back to the 1880s, more than 130 years ago, we can determine your name going back a long time. Here we see that your name in the 1900s would be Sarah if you were Jennifer in 1994. You'll need to write programs to make conclusions about the names that we've outlined here, turning all that data into information. The US government releases baby name data every year. We've collected that data and made it available to you as part of this course. We would be excited to have your help to collect similar data for other countries in the world. We have data for males and females going back many years with a different data file for every year. The files share a naming convention, which is convenient when writing programs to open the files and read them. You'll leverage the common naming convention in writing code to access these hundreds of data files. The file contents are also similarly formatted. That will help you write more general code to solve these problems. We'll look briefly at the data file for 2014, the most recent data provided to you for use. The line numbers in the file are ordered by the number of babies with a given name, so that the most popular baby name comes first, then the second most popular, and so on. As you can see here, 20,799 babies were named Emma in 2014, making it the most popular female baby name that year. All the female names precede the male names in the data file. This means the most popular boy's name, which was Noah in 2014, with 19,144 boys named Noah, comes just after the girl names that the fewest girls have, which were Zeriona and Zariah in 2014. We'll walk through the high-level concepts for accessing data in one file, but you'll need to go through the full 7 steps to solve the problem we're asking you to address in this mini project. You'll use several classes from the edu.duke and org.apache.commons packages in developing your solution to this problem. For example, you'll need a file resource object to access the data in a file for a particular year. You'll need a CSV parser by calling getCSVParser method from the file resource class, making sure that you ask for a parser with no header row. Because there is no header row, you'll need to access the data in each record by indexing. The first data element with index 0 is the baby's name in the file. The gender of the baby is the second data element. Once you've got this, you'll be ready to start thinking about the problem and using our 7-step process to solve the entire problem. Have fun! Now that you've learned about the problem that you're going to be solving for your mini project, let's take a look at the data files and some code for working with those data files to get us started in working through the problem. For this first example, I'm just going to go ahead and print out some basic information about what's in the data file so that we can get to know it and make sure that we understand what's going on. So I'm first going to make a file resource, and I'm going to choose which file I want to go ahead and open. And then I'm going to create a CSV record. And I'm going to iterate over all of those records in the file by using the CSV parser that we've seen several times. But in a new twist, as we saw in our video, we're going to put the data value false when we create the CSV parser, and that means that this CSV file does not have a header row. In other words, the very first line of the file is actual data that we're going to be using instead of the header row. For each record that we iterate over, right now we're just going to print out the basic information about it in a nice format so that we can kind of read it and make sure. So I put spaces in between the names. And again, which is different than we've seen before, we're going to be accessing our information using numbers instead of names. And that's because, again, we don't have a header row, so that we're doing it by value, where 0 is the first one and 1 is the second one and 2 is going to be our third one, which is all of the fields that we're going to have in our data. So that's it for our first version of this program. We're going to compile it and run it on a data file that I've created that is meant to be a very simple example just to get us started. And you can see that Emma is the name right here. Emma's gender is female, and there were 500 girls named Emma born in this example. The second one, Olivia, female, 400 born, all the way down to Ava, who was the last ranked girl with 100 born. Noah is the first male born with 100 born, so he was the most babies born, so he's ranked number 1 in terms of male births, even though he appears as the 6th name in the file. So it's all females first, and then all males following that according to their rank. So 1, 2, 3, 4, 5 in our example file, 1, 2, 3, 4, 5 in our example file. So we have 5 girls and 5 boys. You can see the actual data file that I've created here in this spreadsheet where I've loaded the data up. And again, there are 5 females and 5 males. And this is what the data file would look like on a small scale so that we have some numbers we can test with. Here's an actual data file where this is for the births in the year 2014. And you can see that Emma, again, is the most popular, but with 20,799 births instead of the 500 that I made. In this particular example, I've gone ahead and calculated the totals just to give us a sense of how large this file is. And you can see from the total names, there are 33,044 different names in this file. That means there are 33,044 different lines in this file because each name occurs on a separate line. Of those, 19,067 are girls' names, so that means the first 19,067 lines in the file are the girls' names, and then the 19,068th name in the file is Noah, who is the highest ranked boy for this year, and he would be first of 13,977 boys' names that appear throughout the rest of the file. So we're going to be working for our examples with this small file right here, just so we can get a handle on it, because 19,000 and 33,000 are big numbers that I can't really work with and test very easily, but we're going to use these for our testing purposes. So just again as a simple little thing to try, we're going to go ahead and only print out the names if the number born is under a certain value. So I'm going to go ahead and create an integer from the string that we get back for the number born, and so that's going to be the second piece of information. And then I'm going to check if that number born is less than or equal to, say, 100, and then print out those names, only those names that are smaller than 100, and so let's see what those are going to be. So now when I compile it and run it with that same small data, I see that I get Ava, who was the last ranked girl, and all of the boys' names that were in there, because all of the boys' names had num born less than 100. Now that we've seen the basics of working with these files, let's go ahead and solve a real problem, calculating the total number of babies born, total number of boys and total number of girls. In this case, I've created a new method, total births, for us to work in. In this case, I'm taking a file resource instead of having us choose. That'll make it easier for us to test and work with later. But I'm still going to use the same basic idea that I used in the previous one of looping over, in the previous problem of looping over all of the CSV records in the file. And I'm still going to pass false because it has no header row. So now what we're going to do is we're going to check out the number that were born each time, but we want to add that to a running total of how many were born. So we're going to create a variable called total births, and we're going to add to that the number born at this iteration of the loop. The problem with writing this piece of code here is that we can't both declare a variable and add on to it for this iteration of the loop in the same line. So we have to declare the variable someplace else, and the right place to do that is at the top of the method before the loop is ever started with an initial value of 0, meaning we haven't seen any births, and then at each iteration through the loop we calculate the total number that was born, or add to the total births the number that were born for that particular name. And then at the end we're going to print out the total number of births to see and verify whether or not we got the right thing. So let's just, again, run our simple little function just to see if it's going to work. Now in this particular case, since we've been passed a file resource, we need to have a test method that allows us to choose which resource we're going to be using. We're not going to have a dialog box pop up this time because we already know what we want to work with. We've got that nice small example file that we're going to work with. So I've already put that information in there, and I've already called total births to make sure that we're going to be able to see our output. Since our code compiled, I'm going to go ahead and create a new instance and call test total bursts, and I get that the total bursts were 1,700. And again, if I look back at our example file, I'm adding 500 plus 400 plus 300 plus 200 plus 100 plus 100, 40, 30, 20, and 10. I've added all these numbers up. I don't trust myself to do math on the fly, so I've created in this spreadsheet, I've created a formula that will do the calculation for me, and it came up with the number 1,700 as well. So I feel pretty confident that this basic piece of code is doing what I want. Let's revisit this code and look at the total for total number of boys born and total number of girls born. In order to do that, we're going to have to divide up the children based on their gender. So the way that I'm going to do that is I'm going to check and see if the gender is a certain one. So I'm going to say if the current one dot get of 1, because again the second field is what represents the gender, and if that equals male, say for example, then I want to add to a total for the total boys. So equals the number born, and otherwise I want to add 1 to the total girls instead. Obviously I need to create those variables, and again on the assumption that only whole numbers of babies were born each time, I'm going to go ahead and make those ints, and I'm going to initialize all of the variables up here. And then again I'm going to add a print statement down here to make sure that we're checking our information. I'm going to compile quickly to check that I didn't make any silly mistakes and try testing this again. And now I get 1700, 1500, and 200. 1700, 1500, and 200. So I think again that I feel somewhat confident that it seems to be working. But just to make sure, I'm going to try it on a larger data file. So instead of example small, I'm going to try it on the year 2014 and try running that one. And in that case, I get 3,670,151, 1,768,775, 1,901,376. I've done the same trick in my spreadsheet over here with letting it do the sums, and I see that I get the same numbers for total births, girls' births, and boys' births as what I calculated in my program. So again, I feel relatively confident that my solution is correct. In this code, an interesting question is, does it matter how the boys' and girls' names are organized in the file? That's right, it doesn't for this code. For this code, since we check the gender each time, I could have the boys' names first and then the girls', or I could even have the names interleaved. But in your files, all the girls' names are going to be first and all the boys' names are going to be second, and that's going to determine how you figure out what their ranking is. Since we weren't worried about ranking for this particular program, we didn't have to worry about that distinction, but you will in your code. Good luck with the mini project.
Welcome back. In this lesson, you're going to look at the problem of converting images to grayscale. This is an example of solving a real problem by writing two programs and combining them into a single program. Why might you want to convert an image to grayscale? There are several reasons. You may want to see how images would look if you print them in grayscale. Grayscale printing is much cheaper than color printing, and some publications require that all images be converted to grayscale. Or you might be planning to do some other, more complex image processing. That processing could be simplified or even sped up by working with grayscale images. If you just need to convert one image to grayscale, the easiest thing might be to use an image editing program you already know. You'd open the image, the one you want to convert, and then you'd use the program to create a grayscale copy. But what if you need to convert many images to grayscale? It can be quite tedious and time-consuming to open each image up, transform it to grayscale, and then save it. For a few images, this may not be a big problem. But what if you need to operate on 1,000 images? It would take days to do this by hand, if you could even make yourself complete this repetitive task over and over and over. Instead, you could write a program to convert many images to grayscale. In particular, you might ask the user to select some group of images to convert. Perform the grayscale conversion on each of the selected images, and then save the results using file names which were similar. In our example, you'll add a gray dash prefix to the beginning of each image file name to distinguish the new grayscale copy from the original. This is exactly what we're going to work with you on in this lesson. In particular, we're going to break this large task down into a few smaller tasks. One aspect of the problem is to allow the user to select a group of files and to do something to each of the selected files. While you ultimately want to convert image files to a grayscale version, we'll start out by simply printing the selected file name, a small step toward the solution to the larger problem. Next, you'll work through how to convert one image to grayscale using our 7-step process. After that, you'll combine these first two ideas in programs, into a single program that allows the user to select many files and converts each of these files to grayscale. Finally, you'll make your program save the results to new files with the appropriately named file names.
Welcome back. You're currently learning how to convert a bunch of images to grayscale. An important component of that process is the ability to convert one image to grayscale. In particular, you want to take a color image and produce an image that looks like it, but only uses shades of gray, not any colors. As with all programming problems, the way you want to approach this problem is with the 7-step approach you've learned previously. The first step is to work an instance by hand. As always, we must work with a small, manageable problem size. Here, we picked a 2x2 image to work with. We're going to want to make a 2x2 image for the output, but how do you figure out what shade of gray to use for this pixel? You need domain knowledge before you can proceed. In this particular problem, the knowledge you need is about colors or graphics. The first thing we need to know is what precisely is a shade of gray. A color is a shade of gray if its red, blue, and green components are all the same. However, this knowledge by itself is not sufficient to tell you how to come up with the shade of gray for a particular color, just that the result needs to have the red, blue, and green all the same. One way you could do this is to average the red, green, and blue components. Or you might decide you want a weighted average because the human eye does not perceive all colors in the same way. There could be more complex alternatives. However, just taking the average works pretty well and is simple. Now you have the domain knowledge required to do this problem yourself. You can look at the RGB for a pixel, compute the average, and color in the output pixel appropriately. Then you would go through looking at the RGB values for each input pixel, computing their average, and coloring in the output pixel accordingly. Once you have colored in all of the pixels, you've worked an instance of the problem yourself and are done with step 1. The next thing you need to do is write down exactly what you just did. I started with the image I wanted, which we called inImage. Then I made another image of the same size, which we called outImage. I computed 255 plus 0 plus 0 divided by 3, which was 83, and I made the first pixel of outImage have red, green, and blue values of 83. And then I went through each other pixel, computing the average of the R, G, and B, and coloring the output pixel accordingly. Once we finished this, we had these 10 steps that we used to solve this particular instance of the problem. Now you are ready to move to step 3 and look for patterns and repetition. You can see that we are doing very similar things to each pixel, but they are not quite the same. We need to find the patterns in the number to generalize these steps to any image. Let us look at the particular numbers we need to generalize. Why did we use 255 here and 0 here? These numbers were all the corresponding pixel in inImage's red component. What about these numbers? Similarly, these were the green component of the corresponding pixel in inImage. Lastly, these numbers were the blue component of the corresponding pixel. Next, you should give a name to the result of this math. It won't always be these particular numbers, and you will want to be able to refer to it precisely. We'll call it average. Okay, now that we've thought that through, you can write the general algorithm. Notice how we thought about what we do for each pixel and wrote down general steps. Now we can write this in terms of steps to do to each pixel in the output image. It will work for any size image with any colors. The last thing you should do before you write code is to test your generalized algorithm out on another small input. Here is a small image and the RGB values for each pixel. Take a moment to execute the algorithm and see if you get the correct answer. Yes, the answer is right, so you're ready to implement it in code. Now that we've developed our algorithm to convert to grayscale, we're ready to write code. We've started here with a class for the grayscale converter, and we've already imported edu.duke.star. And before this video started, I went ahead and wrote in the steps that we came up with as comments in our code to guide us as we write. The first thing we did in our algorithm was we started with the image we wanted, inImage. In this case, that's going to be a parameter that we pass to our function so that this function can operate on any image we want. The next thing we did was we made a blank image of the same size as InImage. So if I want to make a new image, I'm going to declare an image resource. We called it outImage in our algorithm. And since I want to make a new thing, I'm going to say new. The type of thing I want to make is an image resource. And when I create this image resource, I need to pass in information, in this case telling it how big I want my image to be. This is going to be the width of InImage and the height of InImage. The next thing we did in our algorithm was we said we wanted to do something for each pixel in outImage. That's going to be a for loop, which you've seen before. Pixel in outImage.pixels. And we're going to put curly braces around all of the steps of our algorithm that we want to do for each pixel. And you can see that BlueJ put this all in pink so we can easily see that these all are going to happen for each pixel. In our algorithm, the next thing we did was we looked at the corresponding pixel in InImage. So what we're going to want to do is InImage.getPixel at the same location as pixel. So pixel.getX and pixel.getY. Now, when we do this, we need to give it a name so we can use it again. That's going to mean we're declaring another variable. So it's going to be InPixel equals InImage.getPixel. The next thing that we did was we said we wanted to compute InPixels red plus InPixels blue plus InPixels green, divide that by 3, and call the result average. So I want InPixels red, which is going to be InPixel.getRed, plus InPixels blue, InPixel.getBlue, plus InPixels green, InPixel.getGreen. And then I want to divide by 3. Now if I write divide by 3 here, I've made a small mistake because order of operations is going to make InPixel.getGreen divided by 3. I want to divide the whole thing by 3, so I need parentheses. And we want to call this average. We're declaring a new variable. What type is this variable? Well, it's going to be just a plain number, so int average equals all of that math. Now I want to set pixels red, so pixel.setRed to average, and similarly pixel.set green to average, and pixel.set blue to average. Those are all of the steps I wanted to do for each pixel. And then our last step at the bottom here says outImage is our answer. Whenever we know the answer to a function, we return that answer. So in this case, outImage is our answer. We just return outImage. So now I'm going to come up here and click compile. At the bottom it says class compiled, no syntax errors. You've frequently been testing your code by just making an object in the BlueJ main window and calling it its methods, but making an image resource there is a little bit tricky, so we're going to write another method to help us test this out. Public void, let's call it testGray, which is going to take no parameters. It's going to make an image resource, we'll call it IR, with new image resource. And that's going to pop up a dialog and ask us what image we want. And then we're going to make gray on this image resource. And then we're going to draw that. Now if we'd forgotten the name of the method we just wrote, we could scroll up and look, but I just remember it's called makeGray. I'm going to compile, again, no syntax errors. We obey the rules of the language. We don't yet know if our code works. Now I'm going to come over here to the main window, and I'm going to hit new grayscale converter. And it's going to give me this object in my BlueJ. Now I'm going to hit test gray. It's going to pop up a dialog asking me what image I want. I'm just going to choose these nice colorful Easter eggs, but when I run it through my grayscale converter, I get Easter eggs in gray. Since my code passed this test case, I'm more confident that it works, And in general, the more test cases we run, the more confident we'll be in our code's correctness. Having written the code to convert one image to grayscale, we'd like to go one step further and convert many images to grayscale. We've started here with the class we wrote in the previous video, in which we implemented our algorithm in code. I've added a method at the bottom, select and convert, which is going to let us select a bunch of files and convert them all. You've already seen this code before, which iterates over a selection of files and just prints out their name. Now we're going to combine these two ideas to give us code which is going to iterate over a bunch of files and convert them all to grayscale. So we're going to start with a very similar structure here. We're going to make a directory resource, which is going to be a new directory resource, and we're going to say for file f in directory resource dot. And if you don't remember this name, you can look at the API or look at the code we did before. It's going to be selected files. And what we did last time was we just printed out f. What we're going to do this time is we're going to convert the image corresponding to that file to grayscale. So I want an image resource in file, which is going to be a new image resource, and I'd like to create this from f. That is, make an image by reading in this file. Then I would like another image resource, which we're going to get by calling makeGray, the method we wrote before, passing in, I called it in file, but I'd really prefer to call it in image since it's actually an image. And then the last thing we're going to do is just draw this file so we can see something happening. So I'm going to compile this, and it told me it cannot find the symbol class file. What we need to do to use file is import java.io.star because that's the package in which files are. Now it compiles fine. And now I'm going to go back over here to my main BlueJ window. I'm going to make a new grayscale converter. And now I'm going to click on this and I'm going to choose select and convert. And it pops up this dialog. And if we navigate through here back to somewhere where there are images, we can now pick some selection of pictures that we would like to convert each of them to. And you can see that it went through and converted each of these pictures into grayscale and drew the resulting image. I think it's still converting one of them. The last one was really big. All right, so now we've put those two ideas together. We've converted any set of images you select. The next step is going to be to save these images to a file.
Welcome. Today what we're going to do is I'm going to show you how to make copies of images by writing a program to do so. I've got a file of images on my computer, and I'd like to actually read some of those images in and make copies of those files. So we're going to do that with a program. So I'm going to create a new class, and we'll call it Image Saver. And we'll go ahead and open the editor. And let's make it bigger. And what we'll do is we'll create a method in here called doSave. So and what we're going to do is we're going to use our directory resource that we learned about. So I'm going to create, if I can spell it right, I'll create a variable called dr of type directory resource. And I'll have to create a new directory resource. And then we will like to loop over and select files from there. So we'll create a for loop and a variable f, which is of type file. And we'll use the selected files method from the directory resource. And let's see what we're going to do with our files. So now what we're going to do is create an image resource. I'm going to create a variable type image resource called image. And that we will have to do create a new image resource. And we'll use the variable f that we read in our for loop. And I want to just make sure this works. So what I'm going to do now is just go ahead and have the image just draw. And so we'll just draw it on the screen and see if this works. All right, so let's see if this works. I'm going to try and compile it. And nope, I've got an error. So let's see what it is. So I forgot to put another curly brace. Whenever you get this reached into file while parsing, and it's got this highlighted, so I'm going to try and add another curly brace. I need one for my method doSave. So let's put that in there. That looks better. And you can also tell the way the colors are lined up that I was missing that. So we'll compile it. Okay. So it's still not compiling because it doesn't know what directory resource is. So I have to import the edu.duke library, so I'll add that right here. Import edu.duke.star, and that should fix that error. So let's compile again. Now it can't find file, so I'm also going to have to import from the Java I/O library. And I'll just go ahead and specify that I want to import the file class. And let's see if that compiles. Yay, no syntax errors. Okay, so now we can come over here and we can actually run this and just see all this is going to do, hopefully if it works, is it will just display some images that I'm going to select. So we will go ahead and create a new image saver. And then we will go ahead and run our doSave method. Now I have to find on my computer where I've got some images, so I'm going to navigate to here. And I've got it on my desktop. I've got a folder of images. There it is. And now I can select several images. I'll just go ahead and select the dinos. And I'll select another one, Easter eggs. I could select as many as I wanted to. And I'll go ahead and open, and our program should just draw these images. And it did. We saw the two images, so that's great. That seemed to work. I'll just get rid of those. And let's go back to our program now, and now what we would like to do, we know that we can get the images and we can display them, and so now what we'd like to do is we'd like to make a copy of them. So we're going to add some more code in here. And let's see, okay, so now what we're going to do is, first what we're going to have to do is we're going to get a file name from the image file that we have just grabbed. So I'm going to create a string for that file name, and we'll just call that fname. So the image, we can use the image resource method that is called getFileName. And if you didn't know about that, you can look in the documentation and you'll see all kinds of methods that you can use with the image class, image resource class. So just get file name should get me a string. And then what we want to do is we want to create a new name, which is going to be like copy with the old name. So let's create another string variable. This will be called the new name. And it's going to be, let's make the string copy dash, and then we'll add that to the front of the file name. And the rest of the file name will be the old file name. So let's see, we will call this fname is the old name. So we've created all we've done so far. Well, let's try and run this. Let's see if this works. So if I will just compile this, it compiled with no errors. So let's just run it. We'll come back over here. We will create a new image saver. And we'll come over here and run our doSave method. We can now go pick some files. We have to navigate over to the desktop where my images are in the images folder. And I can grab, let's see, dinos and Easter eggs again. There we go. And we open them. And we got them. And now I also have the images folder right here, so we can just look and see. We created a new name that was copy of, and if we look in the folder, I don't see any image that's called copy dinos. So we created a string, but we didn't actually use the string to create a new file yet. So let's do that. So we have the name, but now we need to use it. So we're going to actually, there's another method called set file name. So let's use that. So we'll say image dot set file name. And what we want to set it to is this new string that we created. So let's do that. It's called new name. So that should do it. And now we also, what we didn't do is we didn't save the file. So we have drawn the file, but there's also a method in the image resource class called save. So let's do that too. We'll draw it and we'll save it. And that should save the new file. So let's run this and see if this works. We'll compile it. And then we will come over here and run the program. So we'll create a new image saver. And then we'll run our doSave method. We have to find some images. Okay, and so again, I'll just pick dinos and Easter eggs, and let's open them. Okay, so they're displaying again, but how do we know if it worked? Let's go look in the images folder, which is right here. And if you look in there, you'll see there are two new files in there. One is called copy dinos, and the other is called copy Easter eggs. So it looks like they copied them. Now let's see what happens if we run our program again and we select one of those, or both of those even. So let me get rid of these old images, and let's just run our program again. So I'm running the doSave method. I'm going to the desktop, picking some images to make copies of, and I'm just going to make a copy of copy dinos. And let's make a copy of copy Easter eggs, and we'll also make a copy of, let's see, Roger. All right, so we're going to make a copy of those three files, and let's see what happens. Okay, so we had all those pictures pop up, and we'll just get rid of them. And if we look over here in the images folder, let's see what we have. We have copy dinos, and we have copy Easter eggs, because we made copies of copies, is what we did. And then we also made a copy of Roger, so we also see a copy Roger. So anyway, that's how you make a copy of an image, where we grab the file, we have to create a new file name, and then we save a copy of it with the new file name, but we have to give it a new name because there's already a file with that name. So we added copy dash onto the front of it. Hope you enjoyed that. Thanks.
Hi, we're now done with this lesson. in which you've written a Java program to convert many image files to grayscale, batch processing. During this lesson, you learned how it can be really useful to break a large problem down into smaller pieces, into smaller programs that you can then develop incrementally, making each program work and then putting the correct working programs together. You got more practice writing code which iterates over data. First, iterating over files that the user selected using the directory resource class. And then iterating over the pixels in an image, where you wrote code to actually convert an image to grayscale. Converting the image to grayscale gave you more practice in solving a programming problem using our 7-step method. Finally, you put the finishing touches on your batch grayscale conversion program by making it save the new images with file names that were similar to the old file names. This is a reasonably complicated program, and you should be proud of having made your way through this lesson.